Welcome, everybody. My name is Luis Alvarez Gaume. I'm the director of the Simon Center, and I'd like to welcome you for this particular event. And to initiate the ceremony, I would like to introduce President Richard McCormick to lead the word. Please, Professor.
Thank you, Luis. It's wonderful to be in your building and Jim Simon's building. Good afternoon, everyone. It is a real pleasure to be with all of you today to honor and remember Jim Simons, a remarkable man and an irreplaceable colleague, friend, leader, philanthropist, and perhaps above all, visionary. Marilyn, thank you for allowing us to celebrate Jim in this way, to join with us in recognizing the tremendous impact that he and you have had on Stony Brook. We thank you so much. Although I was not fortunate to know Jim personally, I certainly knew of him. And I can see around me, right here, for example, but also all across the university, signs of his enduring impact and of his vision. Jim's devotion to Stony Brook was vast and strong. He shared with us his love of mathematics and physics, and he shared his wisdom, his leadership, and his extraordinary generosity, precious gifts that will last for generations. Indeed, Jim's legacy will prevail for as long as this university exists. We cannot talk about Jim's impact on Stony Brook without recognizing Marilyn, whom I've already mentioned, but want to recognize again. Marilyn, you're so wonderful to our university and to all of us. We're grateful for your... Marilyn, we're grateful for your friendship, your incomparable generosity, and for your continued leadership and counsel. Thank you for your devotion to Stony Brook. I want to also recognize and thank David Spergel, president of the Simons Foundation, and all of the Simons Foundation colleagues who are here today, and indeed everyone who made possible the remarkable program that we are about to begin. I now have the honor of introducing Henry Laufer. It has been a great pleasure to meet and get to know Henry and Marcia is here too, whose lives have been linked to Stony Brook and to Jim Simons since 1968. That's the year that Henry and Jim joined the faculty. As many of you know, Henry was a member of the mathematics faculty, as was Jim, and later was a colleague of Jim's at Renaissance. He's also a great friend of Stony Brook, member of the Stony Brook Foundation Board of Trustees. I can think of no one better to begin our program than Jim Simons' close friend and colleague, Henry Laufer.
Well, thank you, President McCormick, for that very kind welcome to everybody and introduction. Hello, Marilyn again. Hello, everybody. I'm Henry Laufer, a longtime colleague and friend of Jim Simons. I was once a math professor here at Stony Brook. Jim hired me, and this large audience reminds me of when I used to lecture to calculus classes, except that you folks are a lot less scruffy than Stony Brook students. But today we shall talk not about calculus, but about Jim. And before starting, I remind you that there are some excellent obituaries out there. I could vouch for the ones in the New York Times and the Wall Street Journal. Also, very soon, the notices of the American Mathematical Society will publish a memorial article about Jim. There, I am one of many contributors. And here today, however, I will crib shamelessly from that article. The upcoming panels are going to discuss Jim and his relationship with mathematics and philanthropy. I will fill in with a brief overview of Jim and business, and even name a few names. So in 1978, Jim Simons left the Stony Brook Math Department to found Renaissance Technologies, which was initially a venture capital company. But he soon partnered with Lenny Baum, and I'll talk about Lenny and some others later, with the goal of doing quantitative securities trading. But after months in seclusion studying market behavior, Lenny came out and he said to Jim, forget the math, let's just buy British pounds. So they did, and that trade was successful. and Lenny and Jim went on to a successful, shall we say, macroeconomic trading career. But Jim still wanted to migrate from human-based trading to computer-based trading. As he later put it, when you have a large, intuitively based position in the Japanese yen against the United States dollar, you wake up every morning and agonize about whether or not to reduce your position. But when you trade quantitatively, you have an easy morning question: should we turn the computer off? So in 1981, Jim Simons partnered with James Axe to form Esprit Day Corp. And to trade quantitatively. Axe's group evolved and was eventually folded into Renaissance Technologies, which became more or less a hedge fund in about 1990. Since then, primarily under the leadership of Peter Brown and Bob Mercer, Renaissance has been amazingly successful in trading equities and other financial instruments. Jim retired as president of Renaissance in 2009. Most hedge funds, such as Renaissance, fold soon after their founder leaves. But one of Jim's great business achievements was to organize Renaissance so well that he continues successfully until now, even as we speak. So I will now reveal 3 of Jim's business secrets. They're actually truisms, but learning these secrets will not help you to become rich because you have to be Jim Simons to execute them. First, identify the best candidates for the job. At Renaissance, this was primarily a search for raw intellectual power. Jim would say to hire people who were smarter than he was. This was a ridiculously high bar, but he and we tried, and here are some examples. So Lenny Baum, I mentioned previously, was one of the 2 top code breakers of his era. When Simons hired Axe, he and Axe were the only 2 award-winning mathematicians at Stony Brook. Later, after Axe left, we needed new blood, and Jim returned to the code-breaking community and hired Nick Patterson, again, one of the 2 top code breakers of his era. The first question we asked Nick upon his arrival at Renaissance was, who are the smartest people that you know? And he answered Bob Mercer and Peter Brown at IBM. When Peter and Bob arrived, we asked the same question, and they answered Stephen and Vincent Della Pietra, also at IBM, and that has continued, and so on. Second secret, after you identify the best candidate, you have to recruit him. Working at Renaissance is not only financially attractive, it is also intellectually satisfying. Jim would rely on this by saying, oh, work for us part-time, or come in just for a few months. Folks would start part-time, but end up working full-time at half pay. And then they would wise up and get paid for full-time. Or they would come for a few months and stay for years. That was Nick Patterson. That happened to Nick. Third secret, be a friend. In my case, Jim never referred to me as his employee or vice president or chief scientist or by whatever title, if any, that I held. I was always his partner. Now I must be a little vague. I know of several business examples where ventures and hires failed, even miserably. Sometimes, though, Jim would still compensate the other person. But in all cases, they remained friends, and sometimes they tried again. So let me conclude on a lighter note. Jim and I were chatting about the reasons for professional success. So I said easy, talent, hard work, and luck. Jim says, no. Good looks and personality. Thank you all.
Hi, I'm Scott Sutherland. I'm the chair of the math department currently, and we're going to start. I want to point out to you, actually, we have a few housekeeping announcements, like this is being live streamed, so please make sure your phone is silenced or off. Off is better. What else? Oh, we had a long discussion about whether there should be a break or not. There will be a break. It should be around 3 o'clock, right? Yes, we will have very brief, because that's all we could manage to work is there will be a very brief break, but if you need to get up, go ahead. Let me point out, this seems like a very long program. It's the same length as the movie Oppenheimer. So, take that as you will. Let's see, what else do I have to do here? I forgot. I have housekeeping. I did that. Sorry, I lost my place. Yeah, so let me point out the structure here. There's really 3 panel sections, which are bookended, well, not all bookended, so on one end in the middle. There are several interspersed public lectures. They are aimed at a general audience. You decide whether you're part of the general audience or not. All the speakers were told to try and keep them very non-technical, but there's mathematicians and physicists giving some of these talks, so, yeah. And so there's 3 sections of panels which correspond briefly to 3 eras of Jim's involvement with Stony Brook. We skip over the era that Henry Laufer already talked about, so we begin with when Jim comes to Stony Brook, and then we have some talks, and then we move on to the 90s or so, with Jim's returning to being involved with Stony Brook and getting involved in philanthropy, and then we move on to closer to the present day. So that's the general structure of the thing. So let's kick it off with the beginning days, and I would like to welcome the university archivist, Kristen Nitre, to tell you about the very early days. I guess pre-Jim.
Thank you, Scott, and good afternoon, everybody. I'm so honored to celebrate Jim Simon's extraordinary legacy today and to provide context about his profound impact on our university's early history. So I have the awesome responsibility of condensing 50 years into 3 minutes, but I will do my best to do that for you. So sticking with the movie theme, we can go in our DeLoreans back to the future, right? And this is 1950 Long Island, which was transforming into a symbol of suburban growth. The Stony Brook campus opened in 1962 to meet the rising demand for higher education opportunities. But in its early years, it looked more like a construction zone than a grand opening, as pictured here in this 1964 aerial view. And to orient you, on the bottom right, we have Nichols Road. And on the top, we have the Long Island Sounds stretching across the horizon. And then in the middle, we have a few modest buildings, which is our campus, which included the library, chemistry, humanities, and Harriman Hall, which housed the math and physics department. The original buildings were small because it's important to remember that between the initial concept and construction, the vision for the campus had changed. In the wake of the post-Sputnik era, SUNY made a bold decision to prioritize science and technology at Stony Brook. In 1965, John Toll, a physicist, took the helm as president. He was charged with not only building the physical campus, but also elevating its reputation by recruiting top scholars and scientists. Toll was successful at attracting distinguished faculty, including Nobel laureate C.N. Yang. Dr. Yang and Dr. Simons would lead groundbreaking seminars that combined physics and mathematics and fostered strong partnerships with Brookhaven National Laboratory to enhance Stony Brook's own research capabilities. When John Toll hired and appointed Jim Simons as the chair of the Department of Mathematics in 1968, he could not have anticipated the impact of his decision. As the youngest chair in the university's history, Simons humorously noted that he was the only one willing to take on the challenge. Over his decade-long leadership, Dr. Simons built one of the nation's premier math departments, but he would always humbly attribute its success to his esteemed colleagues. An interesting fact is that in Stony Brook fashion, the medical school opened in 1971, even before there was a building to house it. But the construction of the health sciences complex on the East Campus further demonstrated SUNY and the university's commitment to advancing research and scientific inquiry at Stony Brook. This era of transformation was fueled by Governor Rockefeller's support for expanding the research facilities. In 1972, 3 large science buildings were simultaneously under construction. So on the left side, you can see the skeleton of the new chemistry building, and on the right are the foundations of the math and physics building. In the 1980s, the footprint of the Stony Brook campus was essentially complete, and the 1990s saw the addition of a beautifully landscaped academic mall with fountains. By the year 2000, Stony Brook had established itself as a leading research institution, a transformation driven by the vision and leadership of pioneers like Jim Simons. Thank you.
Okay, thank you, Kristen. So now we start the first panel. Which way's up? That way's up, good. Which I have 2 people who were there from the when Jim came, Jeff Cheeger, Professor Jeff Cheeger, and Professor Tony Phillips, who were both in the math department shortly after Jim came. Let me start with, missed, sorry. Okay, so let me start with actually Jim himself speaking about coming to
become chair at Stony Brook at such a tender age.
At such a tender age.
After having just been fired.
They were looking for a chair and had been for 5 years without success. They were looking at distinguished guys.
So we're talking about 1968.
1968, yeah. Distinguished guys, and none of them had come along, or at least who were willing to be chairman. So they were kind of desperate, in my opinion. And someone suggested me.
You know who that was?
It could have been Lenny Charlap. And it was very appealing. I had already worked out something where I'd be half-time at Columbia and half-time at IBM Research up in wherever they were, up in Yorktown Heights. I thought that would be a nice sort of continuation of what I was presently doing mathematics on one side, and IBM. Well, sounded interesting. I had that lined up.
Did you have any idea of repeating the half and half?
Yeah, well, that was a half and half deal. But then this Stony Brook thing came up, and it was fascinating to me. I had never thought about being a chairman, but they really needed to build up a department. And I like people, and I like to hire people. I like to not hire. I never hired anyone, but I like to work with people and sort of get things going.
So you're already, that kind of thing appealed to you at that time, of building.
Building something, yeah, definitely. Just like when I wanted to start a company a few years earlier, that was, I liked it.
But I guess Stony Brook was your first experience, actually,
sure.
of building something like that. Yeah.
The guy interviewed me, the provost, was Bentley Glass was his name, and he said something very funny. You know, he said to me, well, Dr. Simon, you're the first person we've interviewed for this job who actually wants it. I said, well, I want it. So they took a chance, and it worked out good, worked out well.
So I should point out that video, and there's another one later, and several, is courtesy of the Simons Foundation. There's, I think, 15 of them, something like that, on their website. Very nice. Check it out. But let's start with Jeff Cheeger, who you already saw both in person and on video, and Tony. Jeff, do you want to talk about what it was like in the early days?
Okay, sure. Let's see, the mic is on. Yeah. An important point is it was a very special time. And this special time didn't last all that long. So 2 key things were it was still in the post-Sputnik era where there was a lot of support for science. And in particular, at that time, there was the feeling that if you went to this new and still unproven place, Stony Brook, if it didn't work out, you could probably leave and go someplace else. So that was a real feeling at that time. And the other thing that was already mentioned was Rockefeller's dream of making Stony Brook the Berkeley of the East. the funds for that were very important, but they ran out around 1972. So it was only a very short period when this tremendous opportunity presented itself. And luckily, Jim was the person to implement it. And there was a feeling that we were really pioneering something, particularly because of all the resources. And Jim, rather than the chair, kind of acted like a ringleader. And there were a lot of parties in those days. Whenever someone came to give a talk that you were thinking of hiring, there would be a party. The parties got pretty wild, as was appropriate for that era. And the emphasis was always on hiring the best possible mathematicians that one could hire. And Jim Axe, who was mentioned, that Jim spoke of Axe as the existence theorem. When we hired Axe, he had already won the Cole Prize, and so it was shown that Stony Brook could hire a great mathematician. So maybe I'll stop for now and let Tony talk.
Okay. So what Jeff is saying gives you an idea of what it was like. First of all, we were all 30 years old, more or less. So it was a youthful and dynamic situation. And Jim was, as Jeff has said, like the ringleader. He was like the co-conspirator with us in forming a great math department. I should say that there was a good foundation when Jim came. There was a small but solid mathematics department here already, and they kept the tenured faculty small just to allow for a possible expansion that I think Bill Barkus, the chair then, saw coming in the future. So the ground was really clear, and we were, during all this hiring and department building, we were still a regular university math department. We were, teaching calculus and graduate students, and we had all the usual agenda was going on. Underneath this hiring activity, John Toll was the president at that point, and he. One thing that made things work well is that I believe Jim had Toll's entire confidence. Toll had brought Yang to Stony Brook. Yang was a very close friend of the great geometer S.S. Chern, and Chern had known Jim at Berkeley. And I believe that the Toll-Yang-Chern connection was really part of what brought Jim to Stony Brook. At least I like to think so. So Toll actually said once, at least the way Jim recounted it to me, if you're hiring at the right level, you have to make 10 offers for every positive response, right? So it wasn't like that, but as Jeff said, we had a lot of, to hire 5 people, you have to entertain 25, say. So there was a lot of entertaining going on, right? Yeah. There was something really special about Jim that made us confident in his leadership. First of all, he was already a world-class mathematician. He'd done some very fundamental work, along with work that he did for the NSA, which I believe is still secret, but which was extremely important. So we knew that he was kind of a big figure in the profession. And also, as Henry has told us, he was a wonderful manager. He really, hired carefully, but he was very, very loyal to the people he hired and always supported them. And so it was a little bit of a family atmosphere there. Also, the department was small in those days, which meant that everybody knew everybody, and we were like, a department of 25 and a department of 60 are completely different sociological animals, right? It was really very intense and very exciting. And then Jim had this extra kind of moxie, which came from, well, for example, he'd gotten himself fired from the Institute for Defense Analyses because he wrote an anti-Vietnam War letter to the New York Times, which got published, and didn't just raise eyebrows, it got him dismissed. Right? So he was a kind of a free agent, but that kind of irreverence for authority, in some sense, right, was part of the charm that we felt really really sort of ideologically bonded with him. I'll let Jeff take over for a while.
Well, one point I wanted to make was, in addition to all the excitement that's been described and all the outstanding mathematicians who were hired very quickly, 10 in the first year and 10 in the second year. So the first year I'm counting as 1969 when I came. And then, as I said earlier, this process slowed down abruptly. So whatever had been achieved during this very short window of opportunity, that was to a significant extent what you were left with. And the math department obviously did extraordinarily well in taking advantage of that. Now, under Jim's leadership, of course. Another point that I wanted to mention was it wasn't just that we were hiring outstanding mathematicians, and we hired quite a few truly outstanding ones. There was absolutely outstanding mathematics that was done at Stony Brook during this period. And in particular, this was when Jim was working on Chern-Simons. It had started a little bit earlier. It grew out of something that was a kind of different problem. Jim came to a big summer institute in Berkeley, very excited about one problem. And he tried to solve it. In fact, the two of us worked on it together, but some term kept cropping up that he couldn't handle. And that term was the Chern-Simons invariant in the most basic special case. And he subsequently always liked to emphasize the point that this is why fundamental research is so important, because as most of you, I imagine, are aware, Chern-Simons became extraordinarily important in physics, and Jim used to say he didn't know any physics. So with fundamental research, he emphasized it's so important because you never know what it will lead to. There was an outgrowth of Chern-Simons invariance that Jim and I worked on at this time. Maybe for those who, most of you who don't know, I was Jim's student. Although I wasn't officially his student at Princeton, I had met him the year before when I was a senior at Harvard, and coincidentally, we both ended up in Princeton the next year. I was a graduate student and he was at IDA. And at some point, although it wasn't my intention when I went to Princeton, I decided I wanted to work on differential geometry, at least give it a try. And there was no one on the faculty who was working on it currently, but a legendary mathematician, Solomon Bachner, had done very important work maybe 10 or 15 years earlier. So he was my official advisor, but Jim, whom I now knew a bit, having been his student the previous year, I thought I would go to see him and ask him if he could kind of be my teacher. And very luckily for me, he agreed. It made all the difference in my life. and that's no exaggeration. So then he and I worked on something together, something he was very proud of, called differential characters. And this was also during that same period. It was, one could say, a cousin of Chern-Simons. So, yeah, maybe. And also, I think you'll hear in the next video about some of the other people specifically that Jim hired, one of whom was Detlef Grimal, with whom I had worked the previous year at Berkeley. And we continued to work together that first year when, as it turned out, we were both at Stony Brook, and we proved a result called the splitting theorem, which I'm quite proud of.
So maybe that's a good time to bring Jim back, well,
Good.
as we can.
Backtrack just a little bit, you know, what your memories are of the atmosphere in the wild and woolly early days at Stony Brook.
Well, we had a lot of money. When I got there, they were flush.
We had a lot of parties.
We had a lot of parties, but I was able to hire a lot of people was the point. So we brought in a lot of young people. 10 people the first year, I hired 10 people the second year, and we had to move some people out, as you say, who were, didn't have tenure. We had some great, it was a great bunch of people, and we had a lot of fun. What really made that year was getting Axe to come. And once Axe had agreed, a lot of people could, that was the existence theorem. One could attract a great mathematician to Stony Brook. So others came, and of course you accepted as well that year.
Yes, Detlef.
And Detlef. Well, Detlef said he'd come if you came, and you said you'd come if he came, but then he said he would only come if Wolfgang came too, and so with three hires in geometry. But
Well, David Evan also.
Oh, David Evan, yeah, I forgot about that. David came that year, yep.
Okay.
So let me talk a little bit about, I just wanted to tell a couple of anecdotes of Jim as a leader in, I guess around, let's see, the archivist can probably remind me, the year that the math tower started building, we had to move from our quarters in what's now Harriman Hall down to South Campus. Okay, so in Harriman Hall, there was a math library, a very nice math library, which in those days, before the internet and everything, you really needed to have the journals and the books at hand. So it was just down the corridor, and we loved it. Now, the question was, when we moved to South Campus, what happens to the library? And the librarians, I hope I'm not offending anyone here, the librarians have this idea that books are to be protected, right? And so they really wanted to get the math collection down in some very secure place in the central library. And of course, we didn't like that idea at all. Well, things went on, and finally, one day, Jim hired a truck. We mobilized the graduate students, and we actually moved the books ourselves from here down to South Campus, right? So that's the sort of thing that, A, we could get away with, and B, we had the initiative to do. It was good for the morale, I think, right? Then another example, this was a little bit later, this was around 1973, so I had been on a inter-academy exchange visit to the then Soviet Union in 1969. And while I was there, my advisor said, you've got to go to Leningrad and meet this guy Gromov. He's really something. So I went to Leningrad and I met Gromov, who was then, I think, just finishing his his second PhD, which they did in Russia. And I met Yasha Eliashberg at the same time, who was a graduate student. These were brilliant guys, right? And I remember we were standing at a board and Yasha says to Misha, what else can we tell them, right? So it was like, they were really, they were wonderful. And Misha gave me a copy of his thesis. In those days, theses in Russia were, there was no Xerox or anything like that. This was a carbon copy where the formulas had been filled in ink by hand by somebody. Anyway, I took it back to the hotel and I realized that, he had really proved this fantastic thing. I remember writing a postcard about it to Jack Milner, who had been my advisor, telling him that there was this amazing achievement in the Soviet Union. Well, I went back to Stony Brook, fast forward a few years, and word comes to me. In those days, there was really no communication. Through his, I think he had a stepbrother, a fellow who lived in Washington, actually, came to see me in my office and said, there's a chance that Misha is going to be emigrating. So I said, well, I thought to myself, if he emigrates, let him come to Stony Brook. So I went to Jim and I told him, there's this wonderful guy and there's a chance that we might be able to get him to come to Stony Brook. And just on the spot, Jim said, okay, go ahead with it, right? So I don't know what it was really like in those days, but there's promotion and tenure committees. There's all these, university apparatus that's supposed to deliberate on recruitment. But, Jim just said, do it. And I did. I sent Misha a carefully coded letter masquerading as mathematics, but implying that if he could leave the Soviet Union, there was a job for him at Stony Brook. And sure enough, 18 months later, here he was. So that was a great achievement. And I don't think it could have happened as easily without Jim's confidence and initiative. And also, I was very grateful for his confidence in me and my judgment. Because in those days, Gromov was really not really well known at all outside of the Soviet Union. Yeah.
Great. Thank you. So I'd like to wrap this up with one more thing. So Erwin Craw was going to be on this panel also. Erwin came at the same time as Jim, just about, and then was at Stony Brook for quite a long time. He was our chair for a while, was a dean, and retired to go work in Math for America under Jim. And I asked him, he couldn't make it because he can't travel, but I asked him, what did you learn from Jim? And this is what he said.
Advice that I have spent the class with the same advice is just listen when people talk.
So I think that's a good place to end there. So I want to thank Tony and Jeff. We're done.
Thank you.
And call. And now Blaine Lawson will tell you something about Jim and his mathematics.
Well, it's a great pleasure to be here. Jim was my friend and collaborator for many years, starting when I was a graduate student in 1967. Now, much will be said today. A little closer? Okay. Much will be said today about Jim's financial wizardry and his philanthropy, but he was also one of the great geometers of the 20th century, the second half of the 20th century. And he was awarded the Veblen Prize. It's the highest honor in that field, the field of geometry, which is only given once every 4 years. And I have to tell you, the field of geometry was center stage, the second half of the 20th century. Now, to his surprise, as you heard, he had a result which churn, which had enormous implications in physics. Now, concerning this result, there's a great story, and it's a Stony Brook story that probably not many people know. There was a seminar here run by Frank Yang where Jim was once a speaker, and that seminar turned out to have enormous implications for research in math and in physics. And it transformed research in these fields, which had been quite separate for years, into one where there was real collaboration at the highest levels. So I'm going to talk about that. I wanted to have that up, but I didn't. So one of the fields that Jim had major contributions to was the field of minimal varieties. Now, what is a minimal surface? It's a surface in space which locally minimizes area. If you take the surface and you move it a little bit, the area goes up. And you can make these surfaces very simply by taking a wire, putting it into soap solution, pulling it out, and the solution forms a film which, to minimize energy, also minimizes area. Now Jim, oh, wrong way. So minimal surfaces are characterized mathematically by a certain local invariant and by differential equations. But we don't really need to say much about that because I think the idea is clear. But I do want to make it clear that this can be talked about in all dimensions. I mean, you can talk about a curve which minimizes length in a space. Or you could talk about something three-dimensional which minimizes volume in some higher dimensional space. Okay, now Jim thought that minimal varieties should actually have a big role in geometry because minimal curves were already center stage. I mean, they were part of of understanding spaces and the influence of curvature. And so it turned out that, you're constantly hitting the wrong thing. It turned out that Jim was right. The decades that followed made that clear. But what he did was to write a paper that sort of gave a lot of the fundamentals to the geometry of this field. And well, you know, the field of minimal surfaces goes back a couple of centuries, and much was known. And we knew how to provide these things in many different situations. But there was a case of smoothness, the things that one got from the people who were doing these, the things that you got were just not very smooth. Well, Jim, in this paper, said that a volume minimizer of dimension n in any space of dimension n plus 1 is completely smooth, provided n is less than or equal to 6. He also proved something called the Bernstein conjecture that I won't go into. And but what is this if n is less than or equal to 6? I mean, most mathematicians would say that's a good start, but, you know, where do we go from here? We want to know what happens in all dimensions. But it turned out that Jim did more than that. He said in the same paper, when n is equal to 7, there's a variety with a simple singularity. It was just something smooth, a product of spheres, and then you take a cone on it, like this. And the vertex of the cone is a singularity. And he said, this particular thing, I'll bet it's actually volume minimizing, 7-dimensional volume minimizing. Well, it wasn't long after his paper occurred that that three outstanding Italian mathematicians said, yes, indeed, it is volume minimizing, and it also leads to counterexamples to the Bernstein conjecture for all higher dimensions. Now, I have to tell you, this was not expected, and it was really game-changing. Now, as good as that is, it was not his most profound work. His most profound work was related to something called a connection, so I'm going to say just a bit about connections. So think about the two-sphere. By the two-sphere, I mean like a soap bubble, something two-dimensional, or a balloon, right? And you have tangent space, tangent planes everywhere on the sky, just the plane that touches the sphere at one point. And in those planes, you can look at velocity vectors that are velocities of curves on the surface. And you could look at fields of these guys. Now, fields of vectors are something that you need to understand in the analysis of geometry, differential geometry. And so you want to take derivatives of these guys. Now, that's what a connection is. It's a way of taking derivatives of these guys. Now, if you don't know what a derivative is, it really doesn't matter. It's part of the concept, part of the analysis that goes into this. Now, associated to this situation, there were important invariants called the Chern and Pontryagin classes, which can be computed from the connection. And when Jim was working on a different problem, and Jeff just talked about this, he came up with this creature in dimension 3. And so he called Chern at Berkeley, who was a friend of his and was responsible for the Chern invariant. And they talked, and they managed to extend this to all dimensions. It was really new. Now, then with Jeff Cheeger, Jim established an important theory of differential characters, and his work on minimal varieties and his work on differential characters is what got him the Veblen Prize. Okay, now I should say that in recent years, Jim and Dennis Sullivan have also been working and establishing really absolutely unexpected results in this theory. I want to point out that this was really deep mathematics that he was doing in his 70s and 80s. So anyway, now, so I mentioned the Chern-Simons invariants, the Chern-Simons form. Why were they so important? Well, there was a seminar that Frank Yang organized at Stony Brook, and it was a seminar that was aimed to get mathematicians and physicists. Something wrong? Oh. Now you can hear me. Okay. So the idea was that mathematicians and physicists should talk to one another more. Okay? And there were rules for this seminar. If a mathematician was talking, only physicists could ask questions. And conversely, if physicists were talking, only mathematicians could ask questions. Well, Jim was invited to talk at one of these. And the most incredible thing happened. They found out that Jim, who was working on connections on principal bundles, whatever that means, I can tell you it's one of the most recondite areas of differential geometry at that time. You know, beginning graduate students never were taught it. And Yang, who was working on gauge field theories, Yang-Mills theories, that he was responsible for. And by the way, as far as I'm concerned, he should have gotten the second Nobel Prize for it. It was fundamental. Well, they were working on the same thing, absolutely the same thing. You don't know how amazing that was, because if you looked at the two things, they didn't look at all alike. I mean, now we know much more. So it was astounding. Gauge field potentials potentials were actually connections on principal bundles. Yang drew up a long dictionary, which he published, that relating terms and theorems in geometry to terms and results in physics. And what ensued? Well, the news went like lightning. Is Singer at MIT, who was found out about this probably from Jim because they were good friends, and then Michael Atiyah found out probably from Is because Atiyah and Singer were collaborators over many years. In fact, together they proved as far as I'm concerned, one of the most beautiful and profound theorems in the 20th century. Anyway, from these two, many mathematicians became involved. Atiyah, Singer, Hitchin spent many years learning modern physics and proving results at the interface. And Atiyah had a student, Simon Donaldson, who used gauge theory to establish a huge result in dimension 4, which together with results proved by Mike Friedman in topology in dimension 4 gave an absolutely shattering outcome. Dimension 4 was unlike any other dimension. And I think physicists always really like that. But anyway, here are this is, that's Simon Donaldson, and that's Atiyah. And just to give you an idea of who these people were, I mean, there's a prize in mathematics, the Fields Medal, which is our version of, in those days, of the Nobel Prize in mathematics. And it's only given once every 4 years. And Donaldson and Atiyah both have it. But there are a lot of mathematicians in Great Britain, 99 and 12, something like that, who have gotten the Fields Medal. But these two are the only two that received a knighthood. So what ensued? At the same time, the physicists began proving deep results in algebraic geometry. It was amazing. People like Witten, Vafa, Nekrasov, Douglas, and many others were doing geometry just like mathematicians. As a matter of fact, Witten got the Fields Medal, the Nobel Prize in math. So we had a conference here to celebrate Jim's 60th birthday. And this was the poster for the conference. And I always liked it because it was entitled Connections in Modern Mathematics and Physics. And you can see the many ways you could take that title. Connections in a mathematical sense, the connections between gauge field theory and then the connections between the new connections in research between mathematicians and physicists. And you can also maybe see a little connection between Jim Simons and Humphrey Bogart. That's all I have to say.
Okay. Well, hi. I'm George Sturman. I'm going to get this straight here. The director of the C.N. Yang Institute for Theoretical Physics, the very same C.N. Yang. The next section of the program will tell the story of Jim's philanthropic investments in mathematics and physics, covering the period of the 1990s, after that hiatus that we heard about from Henry Laufer, to the beginnings of the Simon Center, whose beautiful Della Pietra auditorium we're in right now. So as described in Blaine's talk, Jim's mathematical work was very influential. And although he was busy elsewhere after he left the faculty here, the impact of his work continued to grow during this period, especially in physics through the Chern-Simons results. As a prelude to this section, we'll have our second of total of 4, 10-minute lecture for a general audience by distinguished Professor Dmitry Karzeyev, or Dima Karzeyev, of the Department of Physics and Astronomy. Dima will give us a sense of what Chern-Simons theory means in physics today. So, Dima.
Well, thank you so much. It's a real honor for me to stand here today and to try and describe the enormous impact that the ideas of Jim Simons have had and continue to have on physics. And I will do this by focusing on the famous paper by Chern and Jim that was already beautifully described in the previous talks by Blaine and Jeff. And the paper appeared in 1974, exactly 50 years ago. So today we can celebrate the half-century anniversary of this remarkable discovery. It's a paper on geometry, and we all studied geometry in school. So if you think you know what geometry is, I challenge you to read the first paragraph or even the first sentence of this paper and grasp its meaning, and it's true even for physicists. It's not at all clear if you see this paper, what implications does it have for physics. But these implications, as I'm going to explain, are truly enormous. And of course, we know that geometry provides a foundation for physics. And as Johannes Kepler famously said in early 17th century, where there is matter, there is geometry. And ever since the work of Euclid in ancient Greece, we know that physics happens in geometry of described by Euclid. Ever since Minkowski developed his theory of space-time, we know that the processes that physics deals with at high energies and communications happen in Minkowski space-time geometry. And Einstein taught us that space-time and gravity are one and the same, and the massive bodies deform and curve space-time. And we still make discoveries here, including the remarkable discovery of gravitational waves that was marked by a Nobel Prize to our Stony Brook colleague, Barry Barish. So now, what is the physics that the geometry of encoded in Chern-Simons theory brings in? So we have just heard about the dictionary that Jim Simons and Frank Yan developed for corresponding between differential geometry and physics. And I show it here, so I promise it's the only equation in this talk. And you can see that this translation is really quite simple. So every time you see a Riemannian connection in this paper, you have to replace it by a gauge field, which describes in physics photons or gluons or electroweak gauge bosons. And a curvature tensor becomes a field strength tensor. And once this transition is made, then you realize that the work of Chern-Simons really brings in a new class of gauge field configurations that physicists should be interested in. So for example, if we look at Chern-Simons form shown on the previous slide and focus on the abelian part of it, which corresponds to electromagnetic fields, then this form represents a magnetic helicity, which is a chiral knot of magnetic flux. So you know that magnetic flux can form complicated knots, and so the configurations of magnetic flux can be classified using Chern-Simons invariant. So what is shown here is a trefoil knot, which is a chiral knot, which is different from its reflection in the mirror. And it appears that these knotted configurations of gauge fields are extremely important in physics. They play very important role, for example, in magnetohydrodynamics, in the physics around it happens in the vicinity of solar corona, and there are numerous applications of this idea in physics. So as time evolved, we learned that Chern-Simons theory in fact truly transforms the understanding of gauge fields, which form the basis of the standard model of the universal theory of the universe. And it has become clear that even the vacuum of the standard model represents a coherent superpositions of states with different Chern-Simons numbers. So this has very important implications for the understanding of the structure of the standard model. It has become clear that Chern-Simons theory provides the basis for quantum Hall effect in two-dimensional systems, both integer quantum Hall effect, where Chern-Simons theory effectively attaches a magnetic flux to charges, and fractional quantum Hall effect. So several Nobel Prizes were awarded for this work. It has also become clear that Chern-Simons invariants lead to a new class of quantum topological materials, including topological insulators, predicted by a former Stony Brook student of Peter, Shuqing Zheng. So in this case, you translate the connection to so-called Berry connection in quantum mechanics. There is also chiral magnetic effect discovered here at Stony Brook and Brookhaven, where you create configurations with non-zero Chern-Simons number by putting a three-dimensional chiral material in parallel electric and magnetic fields. And then the decay of this configuration with non-zero Chern-Simons number proceeds through a new kind of non-dissipative electric current. Most recently, the ideas of Chern and Simons led to the development of the field of topological quantum computing, where you can manipulate these so-called anyons that are created by attaching magnetic flux to electric charges and braiding these anyons. There are also ideas on using states with non-zero Chern-Simons numbers as topologically stable qubits. There is really a lot of excitement and a lot of work that is being done here, including by big companies such as Microsoft and Google. So all of these ideas are really affecting the work and the imagination of many physicists and engineers. So as a final example, let me show you this map of rotation measures in the cosmic microwave background. So this is David's field, and there is ample evidence that we have magnetic fields in our universe on galactic and even intergalactic scales. So what is shown here is a rotation measure. So the photons change their polarization when they go through magnetized plasma. And there is some evidence that universe as a whole may possess helical magnetic fields. And you know, the chiral magnetic effect that I mentioned before may contribute to the instability that gives this helical magnetic field to the entire universe. And so it may well happen that our universe as a whole is characterized by a Chern-Simons invariant. And I don't mean this, I mean this quite literally. I mean that the whole state of the universe may possess some Chern-Simons number. So I think this is, you know, perhaps enough to get some idea of why the ideas that Jim and his collaborators put forward continue to influence the work that many people around the world do. And so I cannot find a better way to end this talk, but by going again to ancient Greece and to give you a quote of another famous Greek mathematician who said that geometry is knowledge of the eternally existent. So thank you.
Well, thank you, Dima. We can't get any bigger than that. Well, I'm trying to get away from the shadow of this microphone. So the tremendous influence of Chern-Simons theory that we just heard about forms a backdrop for Jim's engagement with Stony Brook in the 1990s and beyond. Jim began to explore how to ensure that Stony Brook University could continue to make major contributions in the future. The period of high funding, as we heard about, had changed as we got into the 1970s. And going back into the 90s, it wasn't so clear what the future of Stony Brook would be. So some of the milestones of this period will be on a, I believe, here we are, on a slide, which is behind me right now. And we'll touch on some of these. But just to begin, I'll say an early, if not the earliest program that Jim started at Stony Brook is one that Stony Brook can still be proud of, the Simons Research Fellowships, which enable high school students to acquire firsthand research experience over the summer. And so it started in 1984, and it's still flourishing today. Its director, Karen Kiernan, tells us that 48 students took part this year, chosen from a school of over 1,200 applicants. So our panelists for this section are people who work directly with Jim in the planning and implementation of the gifts which are sketched here. It's well recognized that one of Jim's great talents was building a team, and we've heard echoes of that in different ways in which everybody recognizes that. In that sense, our panelists were part of the team. I'll give their current titles as they come up. A list of their honors would take all of our allotted time. So first, it's Blaine Lawson, from whom we heard. So Blaine, who is the Distinguished Professor of Mathematics here at Stony Brook. Martin Roczek, Distinguished Professor in the Yang Institute, the YITP. Dennis Sullivan, Distinguished Professor of Mathematics at Stony Brook and Einstein Chair at the City University. And Peter van Nieuwenhausen, Distinguished Professor Emeritus and former Director, YITP. And Kumran Vafa, Chair and Hollis Professor, Department of Physics at Harvard. So please sit down. Well, dividing the allotted time by the number of panelists, we see that we won't have quite the time for each of us to talk, but to start, Blaine, please tell us how the math instructorship program, which I see up here, it's up here. In the 1990s, there was a program which was one of the earliest, the math instructorships or postdocs. And how did that begin?
Well, I had just become chair of the department. It was in 1995, 96. And Jim contacted me when I took this office because he was concerned about the future of math at Stony Brook. We had had years of budget cuts at SUNY Central, and it was impossible for us to hire for a long time. We still had a lot of the great faculty that he had hired in those early years, as you heard, but they were getting older, and if we were going to continue to have a great department, we needed young blood. And so we discussed possibilities, and I thought we should have, instead of trying to get big guns, which would probably be older anyway, we should establish a postdoctoral program, which all the classical math departments had. Princeton, Harvard, Berkeley, they all had them. And this brings in young people to the department with fresh PhDs that know what's going on at the moment, merging new ideas. They would be full of enthusiasm, and postdocs are really good for graduate students. A postdoc was a graduate student 2 years ago. And so, it's a different kind of symbiosis, and I thought it would be great, and he agreed. And so we decided on this, and there were going to be 3 appointments a year, and each would be for 3 years. So that was 9 new appointments. Now, it took a while to get them all going. But I can tell you that the program was an absolute success. It was transformative, and it made Stony Brook much more attractive for getting tenure-track people down the road, which we did.
So thanks, Blaine. Another initiative was the Simons Endowment for Mathematics and Physics, which is up here. I believe it was 1993 was its beginning. And among other things, it was used for a number of occasions. In fact, when I look back, I saw once it was amounts to each of the units: the math department, the physics department, the Young Institute, and the Institute for Mathematical Sciences, led at that time by Jack Milner and also with Misha Lubitsch now. Actually, once all 4 departments got together and had a conference on quantum computing in the early 2000s. But another of the important things was the lecture series that were funded by this endowment, which involved both mathematics and YTP. I can remember attending some of these with luminaries like Edward Witten that we heard about just a moment ago. So, Peter, you organized the first of the physics lecture series. How did you look on this endowment? This was something that we had no experience with in the past.
Well, Jim played a crucial role in the establishment of the Institute for Theoretical Physics, and especially in the development. So our institute, the Institute for Theoretical Physics, was founded in 1966 with very high ambitions. We got an Einstein chair, and then the idea was, if you have high ambitions, you need to satisfy 3 criteria. The first was you need a famous physicist as central pillar around whom the institute develops. And Frank Yang was found, and that was clearly satisfied. The second condition, if you have a very good institute, is you should make the right choice of subjects. Subjects not only which are topical at the moment, but which in the future will be important. And looking back, I think the right subjects were chosen. But the third thing, which is also important, is you need funding to attract good faculty, postdocs, students, and visitors. In the beginning, that was okay. Stony Brook started with 4 postdocs, our institute, Bill Bardinier, Nieto, and Woki Toom. And in the 70s and the 1980s, there was some success. Supergravity was invented, jets were invented at Stony Brook. So visitors came with their own money on sabbatical, and so we managed to survive. But in the 1990s, things changed. At that time, I was a deputy director, and I discussed with Frank Yang many times about which directions our institute should follow in the future. Ideas were made that we should go to accelerator physics, biophysics, cosmology, but we decided to stay with fundamental physics, supergravity and string theory, QCD, statistical mechanics. At that time, we knew where to go, and we had a famous person around whom the institute was done, but we still didn't have much funding. And I got very worried because I was looking at the top institutes in the United States with whom we wanted to be on a par, Caltech, Harvard, Princeton, and a few others. And in Caltech, they had a Fleischmann Foundation, which had many people visiting, one of which was Martin Roczek. And in Harvard, there was a big endowment, and I was worried that we would be outclassed. But at that moment, Jim Simons came and started giving us some money, $5,000 per year. And using that, I could invite some visitors. And so the idea was I would invite, not I, everybody, we discussed it in the faculty, that we would invite some top scientists, first of all, to know what in other places was being done, but secondly, to establish connections that in the future people would come. So first was invited Edward Witten, who was a prime figure in the field. Then we got Tom Appelquist from Yale. And then we got Kumbro Bafa sitting next to me, and I remember when you came. And then we got Nati Seiberg. And from then on, we had really good connections with top institutes, and we had also information and exchange of science. The support of Jim increased, we could do more, and we got, in the meantime, a fabulous faculty, if I may say. Excellent students came because the faculty was good, so good students came. And so I can summarize in a grateful way, saying that at present, the institute, the Young Institute for Theoretical Physics, is part of the top institutes of the United States, and this is in large part thanks to the support of Jim Simons.
Oh, thank you, Peter. So, yes. Well, but it wasn't only in philanthropy that Jim was getting re-involved with Stony Brook. He was also getting re-involved with mathematics through a collaboration with Dennis Sullivan that was already been referred to a couple of times. So Dennis, can you say a few words about how did that come about? And tell us a little bit about where it went.
Let's see.
Well, you have to get close.
I'm trying to follow the
close to the mic.
historical chronology here. So what year are we at? We're in the early 90s?
Well, we're in the 90s. Wherever in the 90s you'd like to pick it up.
Okay, okay, good, okay. I'm a mathematician, I have to, 1, 2, 3, 4. All right, so early 90s. Okay, so this is, so the first I state what you're going to talk about and then talk about it and then say that you've talked about it? Okay. So, so talking about Jim Simons getting back into mathematics, right? After, well, he left in the late 70s, formed this business and became a kind of legendary character, and then started this philanthropy. But during those 20 years till the late 90s, I didn't see much of him in person, except we did have a 60th birthday of conference here, and people came and gave talks about these connections that we've heard about. And on a walk, Jim revealed that he had a certain question he'd been wondering about. If you have two connections and all of these Chern-Simons invariants vanish, what does that mean about the two connections? And I kind of knew these things a little bit. I'm sort of in another field, But I realized, gee, that question makes sense. And no one that I knew of had thought to ask it before. See, everyone knew if the curvature vanishes what that means, but this is a weaker condition, but a very strong condition. What does it mean? So that was in 98, at the 60th birthday. 38 plus 60 is not 98. Okay.
Also true.
Right, okay. Okay, so then there was a couple other things that happened, like these characters that he had worked on in the 70s. Another construction was made of these in a completely different way in two areas, one in America by Blaine Lawton and his colleagues, and another in France by Pierre Deligne in algebraic geometry, and they all seem to be equivalent theories in appropriate settings and so on. And so Jim, I've heard this from him, that had the idea to try to prove axioms, like Euclid's axioms for geometry. You could write axioms that characterize Euclidean geometry and characterize these theories. And so that happened, and it turned out his idea for proving it was a lot of these pictures you see of Jim at the blackboard, there's a diagram there, and the axiom was this diagram determines the theory. And often these pictures show that. Okay. Then he had an argument for it, but it had a technical difficulty. He needed to know that in higher dimensions, homological cycles could be represented by things without singularities. And it turns out, if that were true, his argument would work. It turns out it wasn't true. And that was a question that I've been interested in since I was in grad school, so we talked about it. And that's how we started working. And the first paper was getting around the singularities and proving that theorem. Okay. And then we worked on some more papers. And the texture of this conversation was interesting for me to learn. First, I was worried because we didn't seem to be going anywhere, because Jim would sort of write down something that was very obvious and then think about it and talk about it, and say, well, if something goes to zero here, it comes from here, then you move over here and then maybe do something else with it, and then, yes, but what the conclusion? And it took me a long time to realize that what he was doing was kind of like, he was like managing. He was trying to get things into the optimal position before he would strike. You know, and then once, and I'll get, and anyway, we wrote these papers over about 10-year period, about 5 papers. The last one, the last step took 2 years while he was doing this sideways thing. And then he got into a position, and finally he started calculating, and he proved something that was non-trivial, unexpected, and it made everything work. That was the last paper. Then, this is the end now. Okay, so I think these, so now we're up to 2018. But before that, these papers maybe figured in his being elected to the National Academy of Sciences in mathematics. And then I remember there was this dinner to raise money for the Museum of Math, and Jim was being introduced as a speaker, and there had been this article in the New York Times about the world's smartest billionaire, and then because of his election to the National Academy. And so so then he was coming up, and I was wondering, how is he going to handle this as he walked up to the podium? You know, it's sort of like too much, right? World's smartest billionaire. So he gets up to the podium, he says, and he has this way of looking with an innocent look on his face, and you just believed he was being serious. He would look up and he said, world's smartest billionaire. Wonder how many billionaires there are in the world. I'd rather be the world's smartest millionaire. You know, spontaneous and brilliant. So we all laughed and relaxed, and It was Jim Simons at his best.
Well, that's great. Well, when I was a kid, there was like a TV show. It was called You Were There. And I thought, where you'd be like, you'd see Socrates or the Declaration of Independence is signed. Well, okay, we were there when Jim and Dennis were putting those ideas together. It's kind of a unique thing. Well, to go back to the Simons Lecture Series, they still, in math, is still actually continuing. But Qumran Vafa, please, thanks for joining us today. You and Martin have collaborated on what was perhaps the catalyst for much of what followed, the Simons Summer Workshops, which are still going. They began in 2003, and they've gone as 2024, and they're thinking about 2025 as we speak. So please tell us something about meeting Jim for the first time. These brought you to Stony Brook for an extended period every summer. And when you first heard about the summer workshop idea, and then we'll have Martin also follow up on that.
Yes, thank you. I believe it was related to the invitation I got in the context of what Peter mentioned about the program they had for the math physics kind of interface where they're bringing physicists to the campus. I think I gave a number of lectures on that in that context. So that's the first time I came to the Stony Brook, in fact. And there was later, I think maybe the same year, a follow-up conference, a birthday conference in honor of Blaine. And there was I think a party in Jim's house in this honor. And that's where I was talking with him, and he was interested in trying to get people to come to Stony Brook, as we heard already quite a number of times. So he asked me point blank, why didn't you come to Stony Brook? And I said, well, I'm happy at Harvard where I am, but he says, oh, so we can't get you here? I said, well, the way he was putting it, it was kind of, I was feeling I have to give a good response to this. I said, I'll be happy to come here, perhaps maybe for a summer workshop, maybe for 1 month at a time during the summers. Okay, it's done, we'll do that. It was that quick and that fast, it moved in that direction. I think next summer we had our first workshop, if I'm remembering correctly, but Martin can correct me if I'm mistaken. So that's the first interactions. Yes.
Well, so to follow up on that, Martin, what was it like to start co-organizing these workshops with Qumran? And how did they develop in the first few years? I mean, at that time, there was no beautiful building to hold meetings or have lunches or new administrative staff to rely on. So nevertheless, actually, Jim said more than once, I think, that the success of the workshops helped pave the way to the next big development. So how did you get it started, you?
Well, I mean, Qumran was largely involved in choosing a few distinguished people to come and visit. And then we had kind of open applications for whoever was interested, and then we would go through and try to, I still have that, what I call the parquet floor problem. You have people's visits of different lengths, and you're trying to fit it together so that we have roughly the same number of people at any time, trying to take different lengths. And everything was completely improvised. We didn't have office space, so we had to sort of stick people wherever we could find space, in the common rooms. The lectures themselves took place.
Martin, you're still doing that.
It's true.
Every summer, you're still doing that.
Well, we
you're
have
doing
office
more
space
than, yeah.
here now, some at least. Not enough, but some. The lectures took place in the math common room. I think the first year we didn't have all the blackboards. There were only the green blackboards at the back, and we had we scrounged chairs for the participants, and we had some few pictures from that. And
it was the same year with the blackout. I think we had the the electricity out for a week.
That wasn't the first year.
This is the first one?
No.
Yeah, that was, whoops.
I remembered that.
Yeah, they were referring to a blackout in 2003, which lasted a couple of days. In fact, I think it was right at the beginning. And we were going to go like to the Port Jeff Country Club or something, and
In the end,
for dinner,
we got
and
there.
everybody just had to
Then
walk
we had
home.
another blackout where air conditioning was out. We had to hide in the basement to try to survive. And the ITP secretaries were phenomenal. They helped with all the organization. And Betty Gasparino, Doreen would bring in snacks during breaks. Cameron particularly preferred fruit and veggies, so we would have carrot sticks and grapes, and she would buy them at the supermarket. We didn't have any catering food services or anything like that. We didn't have the cafe, so lunch was, people had to go and find lunch. I think we had pizza about once or twice a week.
Yes, I should add that the workshops would not have gotten underway if it weren't for selfless dedication of Martin. I think he's really the person who really made it happen.
And then the other thing was we had parties. That's important, of course. These were, in the beginning, some of them were at my house, some of them were at Jim's house. Some of the first ones were, I don't know if you remember, Marilyn, that we invaded you. And later on, they settled down into more of a pattern. But yeah, it was exciting. And the math and the physics was very exciting. The first workshop led to a collaboration between Kamran and Okunkov, who later won the Fields Medal in part for some of the work that was done at that workshop. And so, yeah, it was just a very exciting and improvised beginning.
But it really had big developments, and in particular for Martin, Kubran, or anyone, when was the idea of a unique center for math and physics? When do you think that was first discussed?
Well, I think,
as an outgrowth.
So Jim originally funded us for 5 years for the workshops. Mm-hmm. And we put together a proposal, and then we had to go through, get permission from the president's office, because Jim was considered, special contact of the president's office, and random people from the university weren't allowed to approach him, so we had to get special dispensation.
All right, let's not get into this too much.
But we had the support of the provost and the president. Everything went well. And then as we were approaching the 5th workshop, we were wondering, well, what now? And so we thought about whether we could approach Jim and Marilyn again. And Jim expressed interest in doing something a little bit bigger and something more permanent. And then the discussion started, what form that should take. And there were lots of ideas thrown around. And Dennis and I started meeting with Jim on a regular basis at Renaissance once a week. And we discussed,
Well, thank you.
Theme and so on. Yeah.
Yes. So this was in the context of, there were 2 landmark announcements. The first in 2006, that Jim and Marilyn intended a major donation in mathematics and physics. Followed after these considerations that Martin's referred to in 2008 by a press conference, where there was a picture of a building that roughly, topologically speaking, looks like this one. And that would announce the pledge of a large number specifically for the Simon Center for Geometry and Physics. And in between, Jim involved himself in the development of the idea of the center. So by December, actually, of 2006, when I looked at some of the old emails, the concept and the name were in place. And the center itself opened in 2010. So the center director, Luis, who began this whole event today, later he'll be telling us about the life of the center. So let me just close this discussion, for which, as you could see, could go on for a whole afternoon on its own, recalling a short email exchange in May 12th, 2006. The math chair, who was David Eben at that time, remember, they hired David Eben too. So he was the chair then. And before that, it was Detlef Grummel, who, the late Detlef Grummel, who I had a chance to talk with then. And the physics and astronomy chair, Peter Koch, and then Jack Milner and Misha Lubitsch of the IMS and I sent an email to Jim expressing our gratitude and excitement on that first of what turned out to be many historic, really large-scale gestures of support to Stony Brook University. And that very same day, just a few moments later, really, Jim and Marilyn replied with an email that said, "We have great confidence in your departments and in the university to make excellent use of this gift. At some point this fall, we'll begin to need framing a plan for its development." And that was some of those considerations were what to which Martin referred. So this opened the door to the next period for our departments and for the university. And to close this section and
Hey,
to
George.
compliment, oh yes,
Yeah,
Dennis.
I want to say something because
Okay.
the discussion is, and I know some people have said it before, but when the gift was made and the center started, there were all these meetings, like the building, you were the chairman of the building committee, you went to all these meetings. Jim himself, this hasn't been said enough, besides the philanthropy and the support of science, he actually worked himself day to day to make his projects optimal and to work better. So in the case of the Simon Center, for the beginning years, Jim went to all the meetings about the building and setting it up. He went to all the meetings about its inception, hiring people. He went to all the meetings about its maintenance, its programs, up until the end of his capabilities. He was attending all the meetings. He worked day to day on these projects. He did much more than just support. And we got the impression before that he was some aloof figure that you could only approach. It wasn't true at all. I saw him one day discussing something about the garden with the architect and the estimate, and the guy said 400,000, and he said, "Well, I think it's worth 200,000." And he changed it from 400,000 to 200,000. I mean, he was there trying to make it better day to day, and he was the busiest, hardworking man I'd ever seen. So I just wanted to say that. It's usually not said. Okay.
And that's why we have a panel. So to close this section, and to complement the short lectures about Jim's own work that we heard from Blaine Lawson and Dima Karshea, Kumran will now describe in layman's term an example of one of the exciting research advances made possible by Jim's support of the summer workshops in this case. A short lecture, The Lotus in the Swamplands. So thank you, and go.
Thank you, George. So I have been asked to give a talk about some of the work which was inspired directly by the summer workshop and the philanthropy of the Simons Foundation in setting this up, and later for the Simons Center supporting us. So this is just an example. I should say that there are huge number of papers that have come out from the summer workshop. I think Martin would know the exact number, but it's a huge number, and I'm not going to represent the huge amount of activity. I'm just going to talk about one direction that this led to, which I'm myself more familiar with, and that's just as an example. But to set the stage, let me see if I can go this forward on this. Am I using the correct one? Yeah, I'm pushing it. Okay, good. So, string theory, I'm going to talk about aspects of string theory and Lotus and the Swampland, and it's a tribute to Jim Simons. So we have already heard about his amazing math work quite a bit, and the fact that he initiated this discussion with Yang in terms of the connection between physics and mathematics and geometry and physics. And this gradually evolved to what later became evolution of string theory, which the ideas, in some sense, directly related to it, because a lot of the developments in string theory had to do with topology and what we physicists call anomalies. And anomalies and so on that Luis himself was one of the main contributors with Ed Witten, was one of the foundations which later led to string theory itself. So therefore, the ideas that were kind of evolving from back then gradually evolved to these advances which led to string theory, even though somehow indirectly or something not, you couldn't necessarily trace it easily, but it does. So now, you might have heard about string theory, but I'm supposed to give a public talk, not assuming you know string theory, so I have to tell you a little bit about it. So microscopic world is dominated by quantum mechanics. You know, the atoms and so forth are best described by the probabilistic laws of quantum mechanics. On the other hand, the macroscopic world is described nicely by Einstein theory, general relativity, and it turns out there's a conflict between the micro world, the small things, and the big things. The macroscopic physics does not fit nicely with the microscopic description of it based on quantum mechanics. So that's one of the big puzzles that was facing physicists. And this conflict turns out to be resolvable if we replace the fundamental entities of matter, which are like point particles, with entities which are like strings or extended objects. So in other words, the point, here I'm representing it by this blue dot there, replace it by strings or more generally extended objects. It doesn't have to be one-dimensional extended object. It could be like membranes or sheets. So this idea turned out to be a key factor in resolving the inconsistencies between quantum theory of a microscopic world and quantum and gravity and the large-scale description of physics. Geometry was a center stage again in this whole thing. The geometry of these objects, strings moving around, they span the Riemann surface, and these mathematical aspects of that came again to be very important for physics. So again, this connection between geometry and physics was becoming even more important in the context of resolving these kind of paradoxes. So, but this in addition, you know, you have unify all the particles into strings, vibrating strings of various types, and you have a kind of a unified description of particles. But on the other hand, it required even more geometry playing a center stage, because it predicted that there are extra dimensions that we do not necessarily see in the macroscopic world. They are so tiny that they will avoid detection. Another piece of geometry coming center stage to physics. What is the geometry? What shape they are? How many dimensions there are? What are their properties? How do they impact physics? All these mathematical kind of questions came to bear on physics, and predictions that they will lead to were crucial for us to understand. So we were all eager to explore different connections with geometry and understanding what does it mean for physics. So the thing was, let me just go back here. The thing was that even though we tried to find a lot of geometries which give you good solutions to the equations of string theory for what these extra tiny dimensions are, it turned out we only got a finite number of them. No matter how hard we tried, it turned out that we couldn't get too many solutions. They were limited. Now, this was very surprising because from the viewpoint of the physics of the macroscopic world, you could write down many things which looked perfectly okay. Like, for example, you could have had a universe which had 5 electrons and 10 protons of different kinds, or quarks of whatever and so forth, but they didn't arise, all of these. Very special types of things arose. And this somehow had to do with the geometric properties of these extra dimensions that were very special which was required for stability of the universe. So what were these properties and how was it giving rise to these special things? Well, on the one hand, being limited in the possibilities was viewed not necessarily as a good thing, but on the other hand, it was viewed as excellent because it limited possibilities and led to predictive power. So the more limited the possibilities were, the better chance we had in predicting what could our universe look like. And so that was the angle we took at it. So, in fact, the choices, you see here the choices up there of what are these tiny little spaces that could be there, the shapes here, the caricature of what these extra dimensions were and how they look like, would lead to different kinds of physical theories with different forces, different particles, different masses. And here we are just displaying that by saying each one gives you a point on a landscape of possible would-be universes. Now, the naive possible would-be universes could be a huge amount, but the allowed ones actually were a tiny set, like jewels in a desert. So you had all this possibility that could have been there, but you get only a finite number of them somehow arising. So this picture we basically viewed as the would-be theories which are not realizable by consistent theories, by consistent geometries, we call the swampland, because they look like landscape, but they actually are not. And the good ones, which are a good landscape, are a finite, tiny subset and special types, which our universe, the standard model of our universe, is one of them. So this led to a program of understanding what are these principles that limit us from the viewpoint of our viewpoint in four-dimensional space-time. Can we predict what are these properties that are special to allow something to exist as opposed to belonging to the swampland? In other words, what is the lotus that we are, the universe that we live in, which is part of the good one? What is distinguishing about that compared to the rest of these possibilities that are not realizable? So in fact, these ideas were growing precisely during the beginning of these workshops. So we heard that the workshop started in 2003, and these ideas came to us during these workshops. And in fact, one of the first workshops, this is the workshop in 2006, was exactly on this program. And we were beginning to develop these, and now this has led to a number of different activities over the past 2 decades since then, and it's one of the major areas of research which attracts many young people to doing work on these. And I will tell you some of the things that has come up recently in this direction. So, and one example of how impactful this can be in predicting things for our universe is the following. So in our universe, there's a mysterious and extremely small energy, the dark energy, which is also Einstein famously called the cosmological constant. And it is fantastically small. In fundamental units in physics, it's basically 0.00, and about 120 of these zeros followed by a 1. So it's extremely small, but yet non-zero number. So what does it mean? What does this small number mean? Why is it so small? And what does it relate to in terms of the sizes of these extra geometries of the universe we are talking about? Does it have any relation with that? What kind of predictions does this lead to? In addition to the dark energy, there is this mysterious dark matter, which is much more abundant than the matter we are made of. So there is this mystery of dark energy, and on top of it, dark matter. And we are a very tiny fraction of the energy budget in the universe, like 5% or so. So we are very small in energy compared to the rest of these. Now, what are these other things do? Where are they coming from? Could it have something to do with the extra dimensions, with their geometry and properties? It's a very natural question for us in the context of string theory. Now, one natural option that arises motivated by ideas in the swampland program was that the smallness of dark energy is related to the signaling of one of these extra dimensions to be larger than the rest. So these tiny dimensions are not all the same shape. They are not like all the same size. It could be one of these directions could be larger than the other ones. And it turns out in this context, having one of these at least being larger can lead potentially to these small, fantastically small values we are seeing in the context of the dark energy. And in particular, it leads to, when you try to combine this with other observational aspects, it leads to one of these dimensions to be larger than the rest, and the length scale to be of the order of a micron. A micron is 1,000th of 1 millimeter. So it is small, not atomic small, they're a little larger, but still sufficiently big, much, much bigger than what we would have expected about these other dimensions which we think are actually smaller. So the way you would imagine our universe sitting there would be that there would be one extra dimension which is larger, like across this box if you look at it, and a slice of it, which is a 3 + 1 dimensional slice of it, is where our universe resides. So we are not filling this whole extra dimension, but we are actually sitting somewhere along this extra dimension. Gravity, unlike us, can go everywhere, including this extra dimension. So these wavy things that you see could be viewed as gravity waves going outside where we live. And in fact, in this model, the dark matter can naturally be describable by gravity waves leaking out of our universe, which were produced at the time where the universe was much hotter. So this creation of the dark matter through this process seems to have a natural match with the experimental observations and make additional predictions which could differ from the standard model, and it'd be interesting that, to check whether these are experimentally realized. So one other aspect of the smallness of dark energy would have great implications is that the light tower of these excitations, which are dark matter, which is related to these waves in this extra dimension, can also be directly observed by doing a simple experiment. Namely, Newton famously conjectured or postulated that there is a gravitational attraction between every two massive objects, whose gravitational attraction drops with 1/r², 1 distance squared, as you take them farther away, or they get stronger with 1/r², 1 distance squared as they become closer. If there is this extra dimension, what this means is that as you begin to make them closer than the size of this extra dimension, you begin to feel the existence of this extra dimension. What that means is that if you bring them closer than a micron or smaller, you would expect the force law to go from 1/r² to 1/r³, which would be the corresponding force law in one higher dimension. This kind of experiment actually could, in principle, be done, and it's actually being done by different groups right now. Try to check whether, as you decrease the length scale and measuring the force between particles, does it actually increase from 1/r² to 1/r³? So these would be one of these implications would be, if it's true, it would be one of the most amazing discoveries, the discovery of the extra dimension through this simple kind of experiment. So progress in this field is continuing with rapid rate, and Simons Foundations, as it does in many other areas in science, is supporting this. So we are the beneficiary of the Simons Foundation in many different forms through the creation of these workshops, to the Simons Center, and continuing supporting. And we are grateful to Marilyn and Jim for having initiated all these activities. Thank you.
Well, thank you, Comrade. So we've now actually come to the end of the second section of the three sections in this afternoon. Thank you, everyone, for sticking with us. I will, we're now going to have a short break, believe it or not. And Deborah, our next moderator, that's Deborah Lowenklein, Senior Associate Vice President for Advancement, for whom I might say this event has been a kind of labor of love. Deborah will lead the final session, and in the meantime, we'll take a break of, let's say, 5 minutes. So please stretch, Turn your phone on.
Good afternoon. I'm Deborah Lowenklein, Senior Associate Vice President of Advancement, and it has been my great honor to work with Jim and Marilyn for over 30 years. Now it is my pleasure to welcome Kristen Nitrate back to the stage.
Thank you, Deborah. So I've been asked to provide a few highlights of how Jim and Marilyn Simon's impact on our university has made a profound difference. So as the university entered the 21st century, it aimed to expand academic and research programs, but really began to place an emphasis on improving student life as well. And the Simons, though, unsurprisingly, led this effort even earlier. In 1984, they established the Simons Summer Research Program, providing high school students with opportunities to collaborate with faculty and make meaningful contributions to STEM research. Opened in 2010, the Simons Center for Geometry and Physics has become a global hub for academic collaboration, and it features unique architectural elements such as a sustainable design, an art gallery, and specialized research spaces. The Simons announced a groundbreaking $150 million challenge grant in 2011 to strengthen academic research programs at SUNY University centers, including Stony Brook, as part of a New York State Economic Development Initiative. The Simons Foundation also has supported Stony Brook's collaboration with Dr. Richard Leakey, leading to the establishment of the Turkana Basin Institute, an international research center focused on paleontology, archaeology, and geology in Kenya's Turkana Basin. The Simons also recognize that public art on campus enhances the educational experience, fostering creativity and a sense of community. A notable example of their impact here is Dr. Helaman Ferguson's 24-foot bronze sculpture, Umbilic Taurus. This artwork symbolizes the intersection of mathematics and art and celebrates their harmony. The Medical and Research Translation Center building, and the Stony Brook Cancer Center opened in 2018, providing expanded space for patients and families, research, and innovative cancer treatments. The School of Medicine was renamed the Renaissance School of Medicine, reflecting a renaissance in biomedical research, and supports several centers, endowed chairs, and scholarships and fellowships. The Stony Brook Simon STEM Scholars Program empowers historically underrepresented scholars and students to address global challenges and affect meaningful change. And pictured here are Jim Simons, Marilyn Simons, and David Spergel. And in June 2023, the Simons Infinity Investment was announced, a historic $500 million gift from the Simons Foundation, expected to generate a total impact of $1 billion through matching funds. And pictured here are Jim Simons and Ashvin Chabra. And coming full circle, here's a recent aerial of our campus here at Stony Brook. Jim and Marilyn Simons have been instrumental in Stony Brook becoming a distinguished research institution, all while emphasizing the vital roles of research, community, and philanthropy. Their generosity has left an indelible mark on the institution's legacy and history, and for that, we are infinitely grateful. Thank you.
Thank you, Kristen. So Kristen just showed you one view of campus. I'd like to show you another. Oops. Wait, okay. From the math department to the MART at Stony Brook Medicine, and from Governor's Island to Turkana Basin in Kenya, Jim and Marilyn and the Simons Foundation have strengthened the university and expanded its reach. Impressive, isn't it? We use the word transformative all too often, but in this case, I think it is apt. Now I'd like to ask my third panel to join us on the stage. I'd like to start by introducing David Spergel. David graduated from John Glenn High School in Huntington, and during college did a summer internship at Brookhaven National Lab. So he's no stranger to Long Island or to Stony Brook. After 3 decades as a professor of astrophysical sciences at Princeton, David joined the Simons Foundation Flatiron Institute in 2017. In 2021, he became president of the Simons Foundation. David, I want to ask you about 2 of the important ways you've continued to support Stony Brook since assuming leadership of the Simons Foundation. Can you tell us a little about your hopes and dreams for the Stony Brook Simons scholars, STEM scholars, and the Infinity Investment?
I'd like to do that. Before I do that, though, I want to say a bit more about Jim as a builder and sort of echo a theme that Dennis started, in that Jim liked building stuff. And he approached building things with the same joy he approached mathematics. And he was deeply involved. You know, my first interactions with Jim were helping to build the Flatiron Institute. And Jim really took great pleasure and was involved with the details. And I remember Jim looking at the architect's plans for the Flatiron Institute and recognizing that this room on this floor wasn't right. The size just wasn't right. By eye, he could see that. And this was, of course, sketched by some very junior architect, and the senior people went, no, this can't be right. Of course, Jim was right. And Jim was really paying attention to all the things that were going on and was intimately involved in many of these successes that you're hearing about in these different programs. 2 of the ones I want to mention, 2 of the things that I think of as building for the future. And one is the Simons STEM Stony Brook Scholars Program. And this is a program that grew out of our looking around at ways in which we can encourage a more diverse group of students to go on and thrive and really go on to PhDs in STEM fields. And we looked at the success of the Meyerhoff program, looked at the tremendous strengths there are at Stony Brook, and this seemed like a place where if this seed was planted, it would thrive. And I just want to say how exciting it is to come and continue to meet the STEM scholars and see the seed not only thrive, but really take off. And there's just a tremendous group of young scholars attracted to the program, people who are deeply engaged in science, and students who I think will be leaders in the field a decade, 2 decades from now. And I think this is one more part of Jim's legacy. Right? We've heard this when we talked about Chern-Simons, how insights in mathematics have led to advances in physics that really continue and grow. And even when Jim had moved on to working primarily at building up his business, the impact of his work continued to echo. And I think with the STEM Scholars Program, Stony Brook and the Simons Foundation are enabling students whose work will have impact on STEM fields throughout the rest of the century, right? People who are educated now will be doing great science in years to come across many fields. And it's been a pleasure to meet these students, pleasure to hear about the great work they're doing, and I think that's just a piece of the legacy. Another long-term investment that Jim and Marilyn and the Simons Foundation have made in Stony Brook is the Infinity Investment, which is the largest unrestricted endowment gift. And it's a gift that was structured in a way that its impact is larger. because of the match from the state, and I think most importantly, because of the match with other philanthropic gifts. And one of the goals there is to grow the community of supporters of Stony Brook and to create an endowment that will enable Stony Brook to be an even stronger institution in the future. And it is really Jim's investing in building and structuring and creating things that will be enabling for the future. And this is something that, Jim and Marilyn and really all of us at the Simons Foundation are so pleased to see how these things are enabling Stony Brook to thrive and lay the groundwork for an even stronger and more influential institution in the future.
Thank you, David. Thank you for everything the Simons Foundation continues to do for Stony Brook. Jim believed that a strong relationship between Stony Brook and Brookhaven National Lab was critical to the university's success. He was a passionate supporter of the relativistic ion collider program and championed having the electron-ion collider built at BNL. Our next panelist is Abe Desponde, a distinguished professor of physics, the director of science for the electron-ion collider at Brookhaven National Laboratory, and the interim associate laboratory director for nuclear and particle physics. Furthermore, he is the director of the Center for Frontiers in Nuclear Science, set up jointly by BNL and Stony Brook and funded by the Simons Foundation. Abe, to begin with, can you tell us why the relationship with Brookhaven National Lab is so important to the university?
Yeah, before I go there, I want to continue with what was just mentioned. Those Simon STEM scholars are already making their mark. The first year they came, 2 of them came to our group and we were happy with it. The second batch is now working with our group. So I think they will continue. I completely agree. There's a great bunch of people. I think it's great to have Simons Foundation support this. Brookhaven National Lab is about 20 miles here if you drive from here. It was set up in 1948 or so, along with some of the early national labs that were set up. For those who don't know what the national lab history was, at that time, the Second World War had ended, and universities were coming together. Researchers from universities had to find places to do physics they couldn't do, or chemistry they couldn't do in their own single labs. So people started looking at a bigger picture as to what you can do with federal money coming in to support collaborative research on a very large scale. So that's where we build colliders, we build detectors of large scale, and do particle physics at the highest energy, nuclear physics at the highest energy. So Brookhaven Lab is one of those. It started, as I said, in 1948, and the university was set up in 1962. I'm sure there is a connection there, that there were people of higher education with expectation that their children could go to a university here on the island. Must have been something like that. So it's not completely surprising to me that the university came up around 14 years after the lab started setting up. Now, we have had, there are 8 such labs around the country, which are major labs which are run by universities or consortiums of universities. So I think Stony Brook should be very proud that we have such a place in that running. We are chairing operations of Brookhaven National Lab with Battelle and 6 other esteemed universities like Princeton, Yale, Harvard, MIT, Columbia, and Brown. So this is the group with Stony Brook runs Brookhaven Lab. Now, what are the benefits on the research side? Well, first of all, our students and postdocs who are involved in this multi-dimensional and multidisciplinary lab, they have the world's best technology and the scientists collaborating with them at a 20-mile distance. The alternative was that you could go to CERN 6,000 miles away. Right? I mean, this is a very big advantage that Stony Brook has, and it shows. Stony Brook is one of the largest contributors in terms of people, users of the lab. About 5 to 7% of the users of the lab are Stony Brook employees and faculty and researchers and graduate students. And we have something like 100 joint appointments. So like me, we have 50-50 or some fraction where we actually have that kind of intimate knowledge. So I think it provides a fantastic avenue for students and postdocs to flourish, get into research at a very early stage, particularly for students, And people like us who have, work-life balances, families, you can still don't have to travel all the time to do research.
So tell us some examples of how Jim played an instrumental role in maintaining and expanding that collaboration at BNL.
Right. So this story began with begins with the relativistic heavy ion collider, which was built in the late 90s and operated starting 2001. I came to Stony Brook as an assistant professor in 2004, and I was at Brookhaven starting to build the components of RIC early part. And when a new collider comes through, it takes about 4 to 5 years to bring it up to the level of the full potential operation. And in 2006, so 5 years, exactly when we were going to run our first wonderful beam collisions to do the best physics we could have done with polarized protons, the government announced that the money that was needed was short. I mean, it wouldn't provide us with the full amount of money. It takes about $102 million at that time, $102 million to cool the machine, to pay the people who cool the machine and get it ready. And it takes another $21 million to run it for science. And so they gave us the 102, but did not give us the 21. And I believe, I was assistant professor, this was all what I was told, but I was a run coordinator, so I was very intimately connected with the management as to what was going on. I never met Jim at that time, but what I was told is that in the BSA board meetings, he basically said, it's a waste of taxpayers' money, $102 million of it. Why don't we try to collect the remaining money with our friends who can? And he apparently wrote a $17 million check there and there itself, and another $4 million came from generous contributions from the rest of his collaborators at Renaissance, and that made the $21 million within 2 days. And we were told there was no run, go home, sleep, and I would have been the only run coordinator without a run. But 3 weeks later, we got a call saying that you got to get ready. We have the money and we're going to run it. I think he appreciated the fact that, first of all, I think his instinct was right. The instinct that it was taxpayers' money that could not be, it would have been wasted completely, $102 million without, And more importantly, which I don't know whether he understood it or the people around him, but we understood from the grounds up, that a lot of people would have left the project at that time. These people have built the machine, those people who, would have been so dejected at that early phase of the program. And I believe that without that $20 million or so, I don't think we would have had a successful 25-year, fantastic QCD program using the RIC. We are just running into the last year of operations, but I don't think the 2006 to 2025 would have run without that kind of thinking and that kind of support that came through his generosity. So I wanted to thank him, thank Marilyn, and thank whoever, maybe there are people here who did that contribution to the 4 million.
You got tenure then, right? You got tenure then.
Yeah. Yes, and that was my tenure year too, so it helped.
Tell us about 2020.
2020, yes. So now, as was mentioned, that we are coming to the end of the RIC program. It's 25 years next year, and we are moving into a new collider called the electron-ion collider. Electron-ion collider ideas started developing just as I came here in 2000 or so. There are colleagues of mine at Brookhaven and we got together and said, what do we do beyond RIC? And some of the ideas that we already knew would be unanswered questions, very fundamental questions in QCD. Our knowledge of the nucleus would not have been answered. So we came up with this idea that instead of having heavy ions collide, as the word says, relativistic heavy ion collider, we want to take one of the heavy ions away and put an electron beam in it, and now you do an electron-ion collider. The idea is to actually take pictures, three-dimensional pictures of the nucleus, including the proton, and try to understand the inner workings of it, of quarks and gluons, how they behave. And there are some fascinating predictions of QCD that need to be checked if that is really the correct. So that's what we're going to do. So we presented the case to the science approving bodies in 2015, and they blessed us in 2016 and 18, and then suddenly a race started between Brookhaven Lab and Jefferson Lab in Virginia as to who would build the collider. All these years we were working together. We never spoke about where it was going to be built. They had the electron beam, we had the ion beam. So we thought we would collide them at Princeton and do some physics joke. But in any case, this was how the race began. And I think it was Jim's passion that Stony Brook and Brookhaven had to be successful. So he basically said, what can he do? What could he do to support? And I think he started with that idea. He gave us, at that time, there was no federal funding for any research on electron-ion collider. There still is none. It's all production, build the components, they have money, but not to fund a postdoc. So the Simons Foundation gave us $5 million to start that funding for younger people. So we have used the money entirely to support postdoctoral fellows who want to eventually go and work in this area, both experimentalist theorists and accelerator scientists. And the idea is to really push them into this new field until the Department of Energy is ready to start funding them. So that's what the program is. And I'm very proud we have had 26 graduations of postdocs since 2017 when we started the center. And all 26 are now either tenure track or tenured people at the universities around the world. And they're writing their own grants now for future to work on the electron-ion collider, exactly as we had sought what to do with this, So I think investing in young people was a good idea, and I think this has worked very well. So that's something that we are trying to do now.
Thank you so much. Our next panelist is Luis Alvarez Gon. He received his PhD in physics at Stony Brook in 1981. After spending time at Harvard and BU, he decamped to CERN in Switzerland, where he's a permanent member of the theoretical physics group for almost 30 years. In 2016, he came full circle, returning to Stony Brook as director of the Simons Center for Geometry and Physics. Since the early years of the Simons Center and the ideas behind its development were discussed in our last panel, Luis, I'm hoping you can tell us about the kind of science that the faculty, postdocs, and graduate students do here at the Simons Center.
Well, thank you very much. One thing that I have to say is that, of course, I'm extremely grateful to Jean, Marilyn, and to my colleagues in the Physics and Math department who persuaded me and convinced me to come here. It's been a real privilege to be part of this project. Now, I came the easy time when everything was built, so in a sense, it was relatively easier to run the show. But I think I would like to say that, like many other research institutions, what we do in the Simons Center is essentially basic science. This is science that is motivated by curiosity, not by applications. The goal is to build knowledge about the laws of nature and even those, the basic properties of the realm of mathematics, but without having a particular application in mind. Some people might say that, okay, well, this is useless research. But it's interesting that that useless research has often revolutionized our lives and our economies. And I can give you a few examples, not necessarily those produced in the Simons Center, but maybe. The simplest one that I think comes to mind to every scientist is quantum mechanics. You think about the early quarter of the 20th century, there were some crazy people interested in understanding the atomic structure of matter. There were very few, and they were puzzled by behaviors that they could not understand. Now, that was, of course, great from the point of view of curiosity-driven research. We got into a deep understanding of the structure of nature. But then what came out of it, for example, is semiconductors, transistors, microelectronics, computers, lasers, revolution in communications, radiation therapy, medical imaging, you name it. In fact, the former director of the Fermi National Accelerator Laboratory, Leon Lederman, made a study some years ago. And the estimate was that the gadgets and the outputs of quantum mechanics in technology accounted for something between the 30 and the 40% of the US GNP. Now, you can take that into account with the discoveries in the 19th century about the steam engine and electromagnetism, then you can probably even go above 50% of curiosity-driven research that was considered useless at the time, and without which the US economy would not work. So this is something that we have to vindicate, these aspects of basic science, unfortunately with politicians, but also it's very important to make sure that the general public are aware of these things. A more useless thing than quantum mechanics at the time was Einstein's general relativity. That's something which Dima was talking about, and Qumran. And of course, this is fantastic, curiosity-driven research. It is instrumental in understanding the behavior of the universe as a whole. But what you probably do not know is that the use of special and general relativity are crucial for the working of GPS. Without using the corrections due to special relativity for fastly moving objects and the fact that time runs differently at different heights over the Earth's surface, it would happen that the GPS, this constellation of about 28 satellites that are running around the Earth, would go out of step in 2 or 3 minutes. And the error accumulated every day, would be about 10 to 15 kilometers. Now, I don't need to convince you that GPS is having a huge impact in the world's economy nowadays. Finally, maybe a third application, which is even more useless than science, is number theory. That's probably the queen of useless endeavors. However, if you look at your credit cards, your transactions, your secure communications, this is all based on mathematics that runs back to the 18th century. Remember that there's some famous Fermat's last theorem that was proven in the 90s. It's a very famous theorem. But on the other margin, on the same book, I guess that Fermat was saying that he had found a marvelous proof. He proved Fermat's little theorem. And Fermat's little theorem and some works from Euler justify or generate what is called the RSA encryption code that somehow has been running communications for many, many years. Now, of course, we know much more number theory, and there are more secure and more abstract codes. But nevertheless, without some knowledge of non-trivial number theory and divisibility of numbers, we would not be able to have these magnificent secure communications, or so we hope. So I think that these are simple cases. Another one that just comes to mind is the Nobel Prize in Physiology and Medicine, meaning RNA. Rufkun and company in the early 90s were looking at this little nematode, which is C. elegans, that has 400 neurons and is the model for a huge amount of revolutions in biology. Nobody understood what these guys were doing, but now there is a huge revolution in pharmacology and treatment of cancer, all kinds of things that are based on the understanding the properties of that completely minuscule being that is called the C. elegans. So these examples abound. Now, the center not only provides fundamental research, but we also have a component which is service. And one thing that it works very well is that we run workshops and programs where what is needed is we are inspired by the way the Simons Foundation works, is that all we need is a blurb. A good idea and a good group of people to come and discuss it. Then the Simons Center provides all the support. And that's great. You don't have to really spend months applying, making long applications and so on. So, and this is also a good way that we have a symbiosis with the physics department, with the Young Center for Theoretical Physics, with the math department. So somehow this conglomerate somehow has an enhanced effect on the community thanks to the general support of both the Simons Foundation and the Stony Brook University. Now, if you want to know what our professors are working on, I'll be very brief. And even just to make sure that they keep me honest, I asked them to give me a few lines. But anyway, Zohar, who is not here, unfortunately, he says that I want to understand a bucket of anions. Now, that's a nice thing. Now, anions, well, there is a fundamental theorem in quantum mechanics and relativity, which is that in 3 dimensions, all particles can be of only 2 types. They are called bosons and fermions. Bosons are based on Bose, which is the Bose-Einstein statistics, and that's why it's called bosons. And fermions is because of Fermi-Dirac statistics, so it's fermions. If you look at materials that are 2-dimensional, there's a lot of new discoveries in new materials, topological insulators, graphene, and so on. Then this theorem does not apply. And you can interpolate between bosons and fermions, and that's why they are called anyons. So this is more or less the type of excitations that Zohar is trying to understand. Because we do not, I mean, although we are creating materials with these excitations, we do not know fundamentally what they are. Now, it's clear that this is going to have huge impact in technology eventually, but it's a fascinating problem. And in fact, it complements the things that Dima was saying before. Because at the end of the day, the anyons is just regular bosons that are dressed with a Chern-Simons term. Amazing. So that's what Zohar has been looking into. Nikita Nekrasov has also been using knowledge that we have acquired in the understanding of Yang-Mills theories. So you see, we have always this dance between Simons and Yang. And Yang-Mills theories are, of course, the underlying knowledge or theories that describe the fundamental particles that we know. So the nuclear interactions, the weak interactions, and the electromagnetic interactions, they are all formulated at the fundamental level in terms of Yang-Mills theories. But there are some, again, exotic materials like graphene, bilayer graphene, systems with many other systems with spins and so on, where somehow our standard techniques in condensed matter physics don't seem to work. And what Nikita is doing is precisely using Yang-Mills theories, the knowledge we've gained about their properties, to explain some of this exotic behavior of nature. And finally, John Pardon is our pure mathematician. He's interested in what is, you might call, geometric topology and related subjects. Now, topology is a very interesting science because somehow what it is concerned with is the study of properties of shapes that are preserved under continuous deformations. It's like thinking of space as clay. You can mold it as much as you like, but you should not be able to cut it into pieces. Okay? Now, this has a big history, and what John has been trying to do is to understand some of these properties of manifolds in higher dimensional manifolds are the generalization of points, lines, and surfaces. And of course, there's a huge amount of interesting properties in developing deformations of these structures in any number of dimensions, including infinite dimensions. Now, obviously, John is not interested in its applications. But who knows, maybe 2 centuries from now, when you want to communicate with Mars, you will have to use John's theorems from next month.
I hope so.
So I think that this is, in a nutshell, what we are doing.
Okay. Thank you, Luis. So, Jim was fascinated with questions about human evolution and prehistory. And the Turkana Basin Institute is one of the Simons Foundation's important investments at Stony Brook. Lawrence Martin is a distinguished service professor of anthropology who for many years was also the director of TBI and now serves as its director emeritus. Lawrence, can you tell us about the impact of the Simons Foundation's investments on the science at Turkana?
Yeah, thank you, Deborah. When Jim and Marilyn first got to know Richard and me, Vleaky, and were hearing about the challenges of doing research in the Turkana Basin, it was hard to imagine, but they used to take every piece of equipment, every item of food, all of their water from Nairobi all the way up to Lake Turkana, which involves 4 days of off-road driving if everything goes smoothly. And the sort of level of inefficiency and expense to do that was incredible. So when Richard laid out the concept to Jim and Marilyn of building a research facility on the shore of Lake Turkana that would take care of all of the infrastructure and logistics needs for the scientists to do their work there, they immediately thought that this made perfect sense. And as Dennis commented earlier, Jim and Marilyn were not just people who wrote a check to support a project. I mean, they showed up and they would take an active interest in every stage of the development of the Institute. Jim never missed a board meeting. Marilyn missed one when she became chair of the board at Cold Spring Harbor, which seemed a reasonable excuse. But they were super committed. And I think the fact that people can drive or fly out to the Takana Basin Institute and go out to the field and do their research, not have to worry where food's coming from, not have to worry about their safety, not have to worry about their internet or even their laundry, has just transformed the ability to do science in a very remote part of the world.
So you told me that the scope of science there has really blossomed. Can you tell me a little bit about that range?
Yes, but a couple of really interesting developments. One in astronomy, something we'd never thought of doing, but some astronomers from the United Kingdom came and said that they were interested in building an optical telescope at Takana. And when NASA collided the DART missile with an asteroid, it turned out the best images obtained of that collision were taken from the TBI field station at Illoret. And this has now led to a large European investment of I think 8 million euros in astronomy programs that are training young African scientists to go into the field of astronomy. A second area is climate science and its related impact on human health. The Takana Basin is the hottest place on Earth that's continuously inhabited by people. The average temperature year-round, night and day, is 29 degrees Celsius, about 84 degrees Fahrenheit. There is nowhere on the planet that's 30 degrees Celsius where people live year-round. So this is as hot as people have learned how to live so far. And the opportunity to study the 8 naturally occurring populations there and see how they've adapted to this, because humans not only live there, they flourish there, they've lived there for millions of years, and yet it seems to be right at the tipping point of where human existence is possible. So, talking with our colleagues in the Health Sciences Center, there seem to be some really interesting opportunities to become, expert in what happens to human health at very high temperatures, something which we're all going to be facing going forward.
And can you just tell us briefly what it means for Stony Brook to be associated with TBI?
So when we started TBI, some of the people involved said that the opportunity to tie Stony Brook's name with Richard Leakey and to be involved in building, a preeminent research facility on the African continent was going to position Stony Brook as an international center for scientific excellence. We've had visitors from over 100 institutions around the world to use the field stations in Takana, and many of those people have never been to Stony Brook. Many of those people may never come to Stony Brook, but they all know about Stony Brook, and they all see Stony Brook as a major player because of the fact they come to the TBI facilities that are part of the Stony Brook enterprise. And the second thing is, I think that we have been able to attract faculty and graduate students to come to the university because of the opportunities that TBI presents in terms of research opportunities and access that have enabled all of the departments that we've collaborated with on faculty recruitment to hire people who would not have come just to Stony Brook and would not have come just to TBI. It's the confluence of excellence at a university with incredible research opportunities. So I think it's really helped to promote the enhancement of world-class faculty and graduate students.
Thank you, Lawrence.
Thank you.
So for our last panelist, in 2011, Jim and Marilyn and the Simons Foundation made a historic $150 million gift to Stony Brook. That gift included $100 million for the building of the Medical and Research Translation Building, or MART, and a $50 million matching gift challenge to galvanize philanthropy across the university. And knowing a little bit about Jim's work behind the scenes, I'm sure it wasn't an accident that this gift was announced in tandem with Governor Cuomo signing SUNY 2020 on our campus. By tying it to SUNY 2020 and including a matching gift challenge, Jim and Marilyn magnified the impact of their philanthropy to momentous effect. Now it is my pleasure to introduce Dr. William Wertheim. Bill is the Executive Vice President for Stony Brook Medicine and has been a member of the medical school faculty since 1996. So he's therefore the perfect person to tell us about the impact of that gift on Stony Brook Medicine. So, Bill, it's been 6 years since the MART opened. Can you tell us a little bit about how that's impacted research?
Sure, certainly. So you saw some of the photographs in a little bit of the history. The MART building is a physically beautiful, extraordinarily functional and collaborative space that's allowed us really to recruit some very, very talented scientists and researchers to Stony Brook that I don't know that we would have otherwise been successful in recruiting. I would be remiss if I didn't mention a little bit about the slightly awkward name of the MART building. The dean and senior vice president at the time was hoping to call it the SMART building and name it for the Simons, Jim and Marilyn Simons. And then was told that by Jim that there were more than enough things at Stony Brook that were already named after him. So just in the spirit of him remaining behind the scenes, happy to make sure it got built, happy to create the space, not so happy to put his name on it. And so we're left with a kind of a funny name that we have to translate. But a little bit about the science that goes on in there. So the MART building in part, or mostly houses our cancer center. And the cancer center researchers that are there are doing really tremendous work. We have a few different main areas or pillars for the cancer center. The first is oncogenic drivers and mechanisms of carcinogenesis, which really looks at the molecular basis of cancer development, oncogenes, mRNA, things like that. And that has been extraordinarily productive for understanding cancer biology and giving us an inkling into therapeutics. The second is imaging, biomarkers, and engineering science. And this has really been cross-disciplinary, allowing us to bring people from bioinformatics, computational science, chemistry, and imaging into one group to help us understand better both how to image cancer and image both on a molecular and a macro level cancer, but also compile enormous amounts of data and help us to see patterns where we might not have been able to see them before. The third is lipid signaling and metabolism, and this is a relatively unusual area traditionally in cancer. We actually have probably the premier group of scientists doing research in a kind of lipids called sphingolipids, and they are very important in cancer signals, in the growth of cancer, as well as perhaps a target for treatment. We are also building a population science and environmental carcinogenesis group. Again, we've already attracted some really wonderful scientists in that group, and it's allowing us to build even more. Apart from the four pillars, we also have a cyclotron and a radiochemistry facility, which allows us to build radiochemicals that will help us image cancer in new ways, both in terms of diagnosis and monitoring treatment, and provide us with the radioimmunochemistry that we need to advance treatment. So really, this is sort of multifunctional. And finally, it's an outstanding space to have helped us grow in our clinical trials. So really, it's just a tremendous resource for us. It's a tremendous resource for our understanding, both in basic cancer biology and in therapeutics.
Thank you. So in addition to the building of the MART and recruiting top talent, which I know the building also did, the generosity of Jim and Marilyn and the Simons Foundation has impacted Stony Brook in so many other ways. Could you just tell us a little bit about that, some of the examples?
Sure. So, one of the things I think is remarkable about both the gift and the match is how it really inspired the community to come and get behind the medical center in ways that I don't really know that it had before. And it's really been quite remarkable. And I think that, that recognition really is one of the things that sparked us to rename the School of Medicine the Renaissance School of Medicine in honor of the many, many donors from Renaissance Technology, really that Jim inspired. So a couple of brief examples I want to mention about this. So you all remember COVID. At the hospital, we really had to very quickly pivot, spend a lot of money on resources and supplies that we suddenly became very expensive, and we really had a hard time getting. So we developed the Health Crisis Fund, and thanks to a very generous gift, matching gift from the Della Pietras, we were able to raise over $6 million in just a couple of weeks. This included donors, more than 2,500 donors, some of whom really had never given to the medical center before. So I think that was really wonderful. Another example is in our ability to take care of diseases that maybe didn't otherwise previously have a home. And I'm thinking of the generous Lowry donation to the Polycystic Ovarian Syndrome Center. There really is nothing else like it, and it's really dedicated to rapidly diagnosing and providing appropriate interdisciplinary treatment for people with a condition that often can't find the right care. And I think it will also serve as an outstanding platform for research. I could go on, but I'll stop.
Thank you. And thank you to my panel. I appreciate it. Now, in the spirit of showcasing the deep impact of Jim and Marilyn's philanthropy, it is my pleasure to introduce Dr. Vincent Yang. Dr. Yang is the very first person that was recruited through Jim and Marilyn's philanthropy to Stony Brook Medicine and is now the Simons Chair of Medicine. He is chair of the Department of Medicine and a distinguished professor in the Departments of Medicine and Physiology and Biophysics. An internationally renowned physician-scientist in the field of gastroenterology, Dr. Yang's research has been on identifying the causes and treatment of gastrointestinal malignancies. Thank you, Dr. Yang.
Thank you very much, Deborah, for the generous introduction. And it is an honor to be able to come here, to be able to stand here to talk about the impact of Jim and Marilyn Simons on the Department of Medicine, which, as you know, as many of you know, is one of 23 departments in the School of Medicine at Stony Brook University. So before I start, I want to just also share with you a little bit of anecdote. In a way that's similar to what Dr. Wertheim just mentioned about naming of the endowed chair. So I've arrived at Stony Brook for about 6 months, and the naming of this Simons Chair has not occurred. So I asked my boss at the time to check with Jim Simons about when are we going to do that. And Dr. Simons, being a modest person as he was, said, I don't really need any naming for my chair, in front of the chair. So we went back again. I told my boss this is really important. And so he went back to Jim Simons again and asked for a second time. So Jim Simons said, okay, have Vince give me 3 reasons why I have to put the name Simons in front of the chair. So I basically thought about it. I said, well, the 3 reasons are, number 1 is really a prestige, the Stony Brook University. When I go out there and give lectures nationally or internationally, there's an endowed chair to my title. Number 2, obviously, is represent a significant resource to my own research program. Number 3, the Simons Chair is tied to the chair of medicine, not to me personally. So what it does means that it's perpetually associated with the department chair. It increases the prestige and the attractiveness of the position for future recruit. I'm not about to retire anytime soon, but I think this also is good reason. So Jim Simons finally acquiesced, and we had our first Simons Chair investiture, which is shown on this slide. So this was, as Deborah said, the first investiture for the Simons Chair of Medicine. It was the first endowed chair recruited based on the generous support for Jim and Marilyn Simons. So to my right is the then or former dean, my boss, Ken Koshansky, Dean of School of Medicine. To Jim Simons' left is Sam Stanley, who was the former university president. I arrived in 2011 or beginning of 2012, Ken Koshansky arrived maybe a little bit a year before I did, and Sam Stanley arrived at Stony Brook a year before Ken did. So I can't really speak for the two of them, but I have this feeling that all three of us were attracted to Stony Brook in large part because of Jim and Marilyn's generous gift announced at 2011 UIR. So I really want to just focus on the growth and development of the research program in my department. In large part is due to the Jim and Marilyn Simon's generous gift to the department. This is the growth of the research funding in the 12 years I've been here at Stony Brook. As you can see here, we have a significant growth in terms of national fundings. Most of this funding is provided by the federal government, and including NIH, the CDC, and the Veterans Administrations. And much of this funding is generated due to new recruits. And I must say almost the entire investment that Jim and Marilyn Simons put in our department were used to recruit new physician scientists or scientists to the department. What I'd like to do is highlight a couple of recruitment that we did in the last 12 years or so, which really, I think, illustrate the impact of this significant gift to the development of the research program in our department. So this is my first recruit of a physician scientist, Dr. Sandeep Malapattu, who is a nephrologist, a kidney doctor. So Dr. Malapattu was recruited to Stony Brook in 2013, a year after I arrived, from Mount Sinai School of Medicine. And since then, he has he became a full professor, and he's the division chief for the Division of Nephrology and Hypertension. As you can see here, Dr. Malapattu is an internationally renowned physician scientist in kidney research. And what's illustrated here is a program of kidney research that he has established here at Stony Brook. And as you can see here, in the short time since he's been here, he had amassed over $15 million grant funding, and he has published numerous publications, close to over 60 publications. Importantly, he has mentored numerous students and postdoctoral fellows, many of whom have gone on to attain their own independent position. Dr. Malapattu's research is centered on kidney, and specifically on a number of important pathological processes that are important to understand the origin of many kidney diseases. In particular, he is looking at cell metabolism, including mitochondrial function. He's looking at cell regeneration, looking at crosstalk and endothelial health. And all of these really congregate into understanding the normal physiology of the kidney organ system, and also they explore the mechanism by which disease occurs in the kidney disease. As many of you know that chronic kidney disease is a very significant health burden in this country, with numerous people on dialysis. And Dr. Malapattu's research is really geared toward developing new and novel strategy to regenerate the kidney, in which to avoid, the outcome of end-stage renal disease. Another example I would like to talk about is the recruitment of Dr. Bettina Fries, who is a professor and chief of the Division of Infectious Diseases. Like Dr. Malapattu, Dr. Fries is a nationally and internationally recognized physician scientist in the area of infectious diseases. She was recruited to Stony Brook in 2014 from Albert Einstein School of Medicine. And since she's arrived at Stony Brook, she has also amassed a very successful research program, not just only her own research program, but also for the Division of Infectious Diseases as a whole. So Dr. Fries has obtained many extramural funding, including R01, VA Merit Review, and Department of Defense grants. She has also published greater than 100 peer-reviewed papers in about 10 years or so. And also, like Dr. Malapatu, is equally important that she has mentored numerous junior trainees. And again, many of them have gone on to become faculty members at various academic institutions. So the research program Dr. Fries has established in infectious diseases are very wide-ranging. They study a number of chronic diseases, including fungal illnesses, including multi-drug resistance, which many of you know that is a significant healthcare concern in our system today. They also focus on Lyme's disease, both in terms of origin and also in terms of prevention and treatment, along with many other tick-borne illnesses, which is a very pandemic, sort of an epidemic portion here at the Long Island. Finally, I'd like to talk about my own research program, which is also benefit from Jim and Marilyn Simon's generous donation. We were able to use some of the resources that were provided when we first moved to Stony Brook to build a very successful research program. As Deborah mentioned, I am a gastroenterologist, and my area of interest and passion is about GI research, gastrointestinal research. So this is kind of a snapshot of what we are doing in our laboratory. So really, there are two major themes in terms of our research focus. One is to study the normal function of the GI tract. The other is to study and understand the abnormal state of the GI tract. So for the normal process, we want to understand how stem cell functions and how cells are replaced in the ongoing basis. And in the process, we'll call homeostasis. In the abnormal part, we are focusing on primarily the gut tumors, specifically colorectal cancer. We're trying to identify the molecular mechanism that leads to the formation of colon cancer. And importantly, we're trying to identify novel therapy for such a for colorectal cancer, which is the number 3 cancer killer in this country. Along with the rest of some of our other physician scientist recruit, our program has been quite successful, particularly after arriving at Stony Brook. And we have, as myself as the PI, have attained over $12 million of extramural funding in the last 10 years or so. And we have also published many papers, many of which are geared to some of these areas I talked about. And also, equally important, we have mentored many students, including MD, PhD, postdoctoral fellow, medical students, undergraduate students, and even some of the high school students, many of whom were funded by the Simon's Summer Research Scholarship. So I'm very proud to say that at least one of my students who went through the summer of research program ended up going to Harvard University, is now a medical student at Harvard Medical School. I'm very proud of that. Still kept in touch with her. So in the last two slides, just want to really illustrate a little bit about what our current effort has been in terms of research. So in this particular project, we wanted to look at the way how intestinal cells regenerate itself, especially after injury. So this is a cross-section. Sorry, go back. This is a cross-section of a small intestine of a mouse as a model. So we study the intestinal epithelium, which is the layer, a single layer of epithelial cells, you can see that lines the innermost layer of the gut organ. These cells actually provide the fundamental functions for our digestive functions. They are responsible for digestion, absorption, and transport of the nutrients that we need on a daily basis. Unfortunately, these cells are also susceptible to all kinds of injuries, infection, and so on and so forth. And fortunately, our body actually has a very good propensity of regenerating these cells after injury. And our goal really of this project is to understand the mechanism by which this regeneration is controlled. And by doing so, we hope to identify a new form of therapy that we can use to help our patients with GI diseases. So in this particular model system, we use gamma X-ray to damage the small intestine. And let's see. So this is a time course of the small intestine after irradiation of a mouse, as compared to, control over here, which is non-irradiated. So the majority of the intestine is controlled by these area in the very bottom where the stem cell resides. The stem cell continue to divide and replenish the rest of the cells to the top. Following radiation, within the first day or two, these cells will die off. They are very sensitive to injury. And this injury is not limited to gamma radiation. Infections, inflammation, chemotherapy drugs, all can cause damage to the cells. However, in 3 or 4 days or so, there is a very robust regenerative process where these cells become, active again, and eventually can restore to the full normal functions. It's a very highly regulated, robust process. So our goal is really try to understand what exactly is making this regeneration happen. So this is what we learned so far. What we have learned that there is actually a loop process which goes between the epithelial cells, which is the sort of the base level of cells, and the underlying tissues we call stromal cells or stromal tissues. So immediately after irradiation, the damaged epithelial cells will produce a molecule, it's a protein, it's called SHH. The name doesn't matter, it's actually Sonic Hedgehog. I don't know why they named that that way. And this SHH molecule is secreted into the underlying tissue, the stromal tissues. And they actually interact and activate a population of stromal cells, a very specific population of stromal cells, and instruct them to produce another molecule, another molecule called Wnt, W-N-T. This Wnt then diffuse back into the epithelial cells and cause the stem cell to start to regenerate. So we are continuing to study this process, so with the hope that we can actually understand and identify new drugs that we can use to help people who have injury who have damage after injury. So finally, I just want to really pay tribute and thanks immensely the contribution of Jim and Marilyn Simons and the Simons Foundation to the growth and development of our department, and we are forever indebted. Thank you.
Thank you, Dr. Yang. In closing, it is my pleasure to welcome Carl Lejwe, Stony Brook's Provost and Executive Vice President.
Thanks, Deborah. What an incredible event today has been. We've really had an opportunity to gain a deeper understanding and appreciation for our history here at Stony Brook, but particularly the way that Jim, Marilyn Simons, and the Simons Foundation have played a crucial role in that. I'd like to thank all of our panelists today. I thought they did an amazing job of real gravitas and rigor, but also in a way that was accessible and really shows how important the work is and how much it is a part of who we are as a flagship university for the state. I want to particularly give special thanks to two of our faculty who played a crucial role in everything that happened today. Scott Sutherland, our chair of the math department. Scott. And George Sturman, director of the Yang Institute for Theoretical Physics. They are amazing scientists, mathematicians, but also amazing people who really understand the importance of humanity and understand the importance of building relationships. And as I reflect on today's discussion and I look where Stony Brook stands, you think about the word legacy, and for one of the very few times that word feels like it falls short. And if we think about the presentations today and we think about the panels, one thing we repeatedly heard was the idea of Jim as a builder. Now, sometimes with the idea of building, we think of this as tangible things. But when I think of what Jim Simons has done as a builder is in terms of culture, a culture where Stony Brook is not afraid to take big swings, not afraid to succeed, not afraid to make mistakes. It is a university that believes it has a strong history, but its best days are ahead of it, and we are coming on the heels of where that is right now. And as we think about that culture, we see that, particularly in the past few years, in some of the amazing successes this university is experiencing and accomplishing. As the #1 public university in the state of New York for the 3rd year in a row, we are truly earning what it means to be a flagship for the state of New York. We're an AAU institution that leads among our peers in many areas that are important to us, but most importantly, our top ranking in social mobility of our graduates and what that means to prioritize equity and access, something that was so important to Jim, is so important to Maryland and to the foundation. Our rise over the past few years, and particularly as a public flagship, is unprecedented, and it would not have happened without the generosity, but also the visionary leadership that Jim has provided and has done as part of our university. So as we think about these successes, we see it in our top-ranked physics and math departments and programs and institutes. We see it in the Simons STEM Scholars, one of the truly great gifts and one of the truly great, and I really love the point, I think it was Louise, someone who had said, we're gonna see the impact of this for tens, hundreds of years. That is truly impact. And in closing, I will say, as I kept thinking about these remarks, I kept coming back to It's a Wonderful Life and the idea of, like, what would Stony Brook be like if Jim Simons was not a part of it? And so I actually put together an entire set of remarks about that. But then I kept coming to the point of, so people gave George Bailey his money and he lost it. That would never happen if they gave it to Jim Simons. So I stopped there. With that said, this is a great university, and we are even greater because of the Simons and the Simons Foundation, and we are going to continue to do amazing things together. Thank you so much for being a part of all of this, and we look forward to continue succeeding with you all as partners.